Hello, and welcome. I'm so glad you found your way here tonight. If you're feeling tired, that's perfectly all right. If your mind has been busy or your body restless, you can let all of that soften now. You don't need to do anything but listen or even just rest while these words move gently around you. Tonight, we're going to explore something ancient and quiet, something that has been resting beneath our feet for longer than we can easily imagine. We're going to talk about stone, about rock, about the layers that build up so slowly, so patiently, that they teach us what it means to be still. If you'd like to follow along on more journeys like this, you're welcome to, but there's no pressure at all. Just be here now and let yourself settle. Let's begin. Beneath the soil where you walk, beneath the grass and the roots and the busy life of insects, there lies a world made entirely of stone. It is quiet there. It is cool. The stones do not rush. They do not worry. They simply exist, pressed together, holding the memory of time in their silent layers. And tonight, we will move through that world together, slowly, the way stones themselves were made. Rock forms in layers, and each layer is a kind of whisper from the past. When sediment, tiny grains of sand or silt or clay, settles at the bottom of an ancient sea or river, it does so grain by grain. One particle drifts down through the water, landing softly, then another, then thousands more, millions more, over years and centuries. The weight of new sediment presses down on the old, and slowly, so slowly, those loose grains begin to stick together. Water moves between them, carrying minerals that act like glue. Time passes, pressure builds, and what was once soft becomes solid. What was once separate becomes one. This process is called lithification, a word that simply means turning into stone. It is one of the most patient processes on Earth. There is no hurry. A single layer of sedimentary rock might represent 1,000 years, or 10,000, or a million. When you see a cliff face with bands of color running through it, you are looking at a timeline written in stone, each stripe a chapter in a story that no one was there to read when it was written. Sedimentary rocks are the most common type of rock you will see on the Earth's surface. They cover about 3/4 of the land, lying like a blanket over the older, deeper stones beneath. Sandstone, limestone, shale, these are all sedimentary rocks, and each one formed in a different way, under different conditions, in a different ancient environment. Sandstone, for example, often forms from the sand of old deserts or beaches. Limestone usually comes from the shells and skeletons of tiny sea creatures accumulated on the ocean floor. Shale forms from mud, pressed flat, and hardened over time. Each type of rock has its own texture, its own color, its own quiet personality. The colors in rock layers can be extraordinarily beautiful. Reds and oranges come from iron oxide, the same substance that makes rust. When iron in the sediment is exposed to oxygen, it oxidizes, and the rock takes on warm, earthy tones. Yellows and browns also come from iron, but in different states of oxidation. Grays and blacks often indicate the presence of organic material, ancient plant or animal matter mixed into the sediment. White or pale layers might be limestone, full of calcium from countless tiny shells. And sometimes you see green, which can come from minerals like chlorite or glauconite, formed in specific ocean conditions. Each color is a clue, a gentle hint about what the world was like when that layer was born. When you stand before a rock face and see these layers stacked one atop another, you are witnessing something called the principle of superposition. It is a simple idea, but profound. In an undisturbed sequence of sedimentary rocks, the oldest layers are at the bottom, and the youngest are at the top. This makes sense, of course. The first layer had to be laid down first, and each new layer settled on top of it. But this principle allows geologists to read the Earth like a book, turning pages made of stone, moving backward through time as they dig deeper. Sometimes, though, the Earth does not leave its layers undisturbed. Forces deep within the planet can fold and tilt, and even flip rock layers, so that what was once horizontal becomes vertical, or what was once on top ends up underneath. These disruptions are the result of tectonic forces, the slow grinding movement of the Earth's crust. Mountains are born this way, valleys are carved, and the neat, orderly stack of rock layers becomes a puzzle, a mystery that geologists must carefully unravel. But even in their disorder, the rocks are still telling the truth. You just have to learn how to listen. One of the most calming things about sedimentary rock is how slowly it forms. We live in a world that often feels fast, where everything seems to demand our immediate attention. But sedimentary rock reminds us that some things cannot be rushed. A single grain of sand, carried by a river, might travel for hundreds of miles before finally settling. It might rest on a riverbed for centuries before enough sediment piles on top of it to begin the process of turning into stone. And that process itself, the slow cementing of grains, can take millions of years. There is no anxiety in this. There is no deadline. There is only the patient accumulation of time. Fossils are often found in sedimentary rock, and they are some of the most wonderful gifts these layers can give us. When a plant or animal dies and is quickly buried by sediment, its body can be preserved. Over time, minerals seep into the bones or shell or leaf, replacing the original material bit by bit, until what remains is a stone copy of something that once lived. Fossils are time travelers. They bring us messages from worlds we will never see, from oceans that no longer exist, from forests that turned to stone long before humans walked the earth. And they do this quietly, without fanfare, waiting patiently in the rock until someone finds them and remembers. The oldest sedimentary rocks on Earth are nearly 4 billion years old. 4 billion. It is a number almost too large to feel. But these rocks exist, and they hold within them clues about what our planet was like in its infancy. The air was different then. The oceans were different. There was no life as we know it. No green plants, no animals, no birdsong, just water and rock and sky, and the slow, steady work of building a world. Those ancient rocks are rare now, worn away by time and weather, but the few that remain are treasures, windows into a past so distant it feels like another planet entirely. Limestone is a rock that deserves a moment of our attention. It forms primarily from the accumulation of calcium carbonate, which comes from the shells and skeletons of marine organisms. Imagine an ancient sea, warm and shallow, teeming with tiny creatures. Foraminifera, coccolithophores, mollusks, corals. When these creatures die, their hard parts sink to the bottom. Layer upon layer, they build up, a slow rain of calcium falling through the water. Over millions of years, this becomes limestone, a rock that is in essence made of life. When you touch limestone, you are touching the remains of billions of living things, all compressed into stone, all part of the same quiet transformation. Limestone often contains visible fossils. You might see the spiral of an ancient shell or the delicate branching of a coral pressed into the surface of the rock. These are not decorations. They are the rock itself, the very substance of it. And because limestone forms in such specific conditions, finding it tells geologists that the area was once underwater, once warm, once full of life. Even if that place is now a desert or a mountain peak, the limestone remembers. Chalk is a type of limestone, but softer, finer. It is made almost entirely from the microscopic shells of coccolithophores, single-celled algae that lived in ancient seas. Each shell is so small you would need a microscope to see it clearly, but together, in unimaginable numbers, they formed thick deposits. The famous White Cliffs of Dover, in England, are made of chalk. They glow in the sunlight, a pale, gentle white, and they crumble easily under your fingers. Chalk is fragile, but it has endured for millions of years, a testament to the power of small things accumulating over time. Sandstone, by contrast, feels sturdy and rough. It is made of sand-sized grains, usually quartz, cemented together. Quartz is one of the most common minerals on Earth, and it is very hard, very durable. When other minerals weather away, quartz remains, and it is carried by wind and water until it settles and becomes part of a new rock. Sandstone often forms in deserts, where wind piles sand into dunes, or along ancient coastlines, where waves shape the shore. The grains in sandstone are usually rounded, smooth by their long journey. You can sometimes see the layers within sandstone, curved lines that show where the dunes once shifted or where the water once flowed. These are called crossbeds, and they are like frozen waves, a snapshot of movement turned to stone. Shale is the most common sedimentary rock of all. It forms from mud and clay, the finest particles, which settle in calm, quiet water. Lakes, deep ocean floors, river floodplains. These are the places where shale is born. Because the particles are so small, shale is smooth and fine-grained, and it often splits into thin, flat layers. This property is called facility, and it makes shale easy to break along its bedding planes. Shale is often gray or black, and it can feel almost silky to the touch. It is a humble rock, not as dramatic as granite or marble, but it holds a special place in the story of the Earth. Much of the world's oil and natural gas is found in shale, trapped in tiny pores between the grains, waiting there for millions of years. Conglomerate is a rock that looks like a mosaic. It is made of rounded pebbles and cobbles, cemented together in a matrix of sand or mud. When you see conglomerate, you know that the environment was energetic, that rivers or waves were strong enough to move large stones. The pebbles in conglomerate are often different colors and types, each one a fragment of some older rock, broken down and carried away and finally locked into a new stone. Conglomerate is a reminder that rocks are not eternal. They break, they travel, they become part of something new. The cycle continues, endlessly, patiently. Breccia is similar to conglomerate, but with one key difference. The fragments in breccia are angular, not rounded. This tells us that they did not travel far. They were broken and buried quickly, perhaps by a landslide, or a volcanic eruption, or the collapse of a cliff. The sharp edges had no time to be worn smooth. Breccia is a snapshot of sudden change, a moment of violence frozen in stone. But even violence, given enough time, becomes still. There is a type of sedimentary rock called evaporite, and it forms in a way that feels almost magical. When water evaporates from a lake or shallow sea, it leaves behind the minerals that were dissolved in it. Salt is the most common evaporite mineral, but there are others. Gypsum, for example, which is soft and often white or clear. In places where the climate is hot and dry, and where water evaporates faster than it is replenished, thick layers of evaporite can build up. Ancient salt flats, long since buried and turned to stone, are found all over the world. Some are mined for salt, some for gypsum, which is used to make plaster. These rocks are the ghosts of vanished seas, the last traces of water that once sparkled under an ancient sun. The process of sedimentation is not always smooth and continuous. Sometimes it stops. A layer of rock is exposed to air and weather, and erosion begins to wear it away. Then, after a long pause, sedimentation resumes, and new layers are deposited on top of the old, eroded surface. The boundary between these layers is called an unconformity, and it represents a gap in the geologic record, a stretch of time that is missing from the story. Unconformities can represent millions of years, entire chapters lost to erosion. But they are not failures. They are part of the process, part of the way the Earth rewrites itself again and again. There are different types of unconformities, each with its own character. A disconformity is a gap between two layers of sedimentary rock, where the layers above and below are parallel, but time is missing in between. An angular unconformity is more dramatic. Here, the older layers were tilted or folded, then eroded, and then new horizontal layers were deposited on top. The angle between them is striking, a clear sign of the Earth's restlessness. And a nonconformity is the boundary between sedimentary rock and much older igneous or metamorphic rock below, a meeting of two very different kinds of stone, two very different moments in Earth's history. When geologists study rock layers, they are not just looking at the rocks themselves. They are looking at the spaces between the grains, the tiny pores where water or air or oil might be trapped. They are looking at the fossils, trying to understand what lived and when. They are looking at the minerals, the crystals that grew in the dark, the colors that hint at ancient chemistry. Every detail matters. Every clue adds to the story. And the story is always more complex, more beautiful than we first imagined. One of the gentlest facts about rock layers is that they're always in contact with each other. One layer rests on another, and that contact is a surface, a boundary, a moment in time. Some contacts are sharp, a clear line between one type of rock and another. Others are gradual, a slow transition where one rock blends into the next. These gradual contacts tell us that conditions were changing slowly, that the environment was shifting over time. Perhaps a river was gradually filling in, or a sea was slowly deepening. Sharp contacts, on the other hand, suggest a sudden change, a flood, perhaps, or a storm, or the arrival of a new sediment source. Each contact is a sentence in the Earth's long, slow story. The thickness of rock layers varies enormously. Some layers are just a few millimeters thin, a single storm's worth of sediment. Others are hundreds of meters thick, representing millions of years of steady deposition. Thick layers often form in places where sediment was abundant and conditions were stable. A river delta, for example, or a deep ocean basin. Thin layers might form in places where sediment was scarce, or where deposition was frequently interrupted. But thickness alone does not tell the whole story. A thin layer can represent a long time if deposition was very slow. A thick layer can represent a short time if deposition was very fast. Time and thickness do not always match, and that is part of what makes geology so endlessly interesting. Rock layers can be traced across great distances. A distinctive layer, perhaps a volcanic ash fall or a layer rich in a particular fossil, can be recognized in outcrops hundreds or even thousands of kilometers apart. This allows geologists to correlate rocks from different places to build a picture of what the Earth was like at a particular moment in time. It is like finding the same page in different copies of a book scattered across the world. The ash layer, for example, was deposited in a single event, a volcanic eruption that spread ash over a wide area. Everywhere that ash fell, it left a marker, a thin gray line in the rock, a moment of fire preserved in stone. Volcanic ash is particularly useful for dating rocks. When ash is erupted, it contains minerals that can be dated using radiometric techniques, which measure the decay of radioactive elements. This gives geologists a precise age for the ash layer, and by extension, for the rocks above and below it. It is one of the ways we have learned to measure deep time, to put numbers on the vast stretches of history that rocks represent. And it is comforting, in a way, to know that we can do this, that we can reach back through millions of years and say, with confidence, this happened then. The study of rock layers is called stratigraphy, and it is one of the oldest branches of geology. It began in the 1600s and 1700s, when naturalists started to notice that rocks were arranged in layers, and that these layers seemed to follow certain rules. They noticed that fossils changed from layer to layer, that certain types of shells appeared in some rocks but not others. They realized that rocks could be used to tell time, that the Earth had a history, and that history was written in stone. This was a revolutionary idea. Before stratigraphy, most people believed the Earth was only a few thousand years old. Stratigraphy revealed that the Earth was ancient, unimaginably old, and that its story was far richer and stranger than anyone had guessed. One of the pioneers of stratigraphy was a man named William Smith, an English canal engineer who worked in the late 1700s and early 1800s. As he supervised the digging of canals, he noticed that the same layers of rock appeared in the same order in different places. He also noticed that each layer contained its own particular set of fossils. This led him to create the first geological map, a map that showed not just the surface of the land, but the rocks beneath it, colored and labeled according to their type and age. It was a map of time as much as space, and it changed the way we see the Earth. Smith's work was not always appreciated in his lifetime, but today he is remembered as the father of English geology, a man who saw the order hidden in the stones. Fossils are the key to unlocking the age of sedimentary rocks. Because different organisms lived at different times in Earth's history, the fossils they left behind can be used to date the rocks that contain them. This is called biostratigraphy. A rock that contains trilobites, for example, is likely from the Paleozoic era because trilobites went extinct at the end of that era. A rock with ammonites is probably from the Mesozoic. A rock with certain types of pollen might be from the Cenozoic. By comparing the fossils in different rocks, geologists can determine which rocks are older and which are younger, even if those rocks are on opposite sides of the world. It is a kind of global conversation, written in the language of life and stone. Some fossils are more useful than others for dating rocks. The best index fossils are those from organisms that lived for a relatively short time, but were widespread and abundant. They appear suddenly in the fossil record, spread across the world, and then disappear. Their presence in a rock is like a timestamp. Ammonites are excellent index fossils. So are certain types of trilobites and graptolites and foraminifera. These creatures may be long extinct, but they continue to serve us, helping us map the deep past, helping us understand the Earth's long story. Not all sedimentary rocks contain fossils. Some environments are too harsh for preservation. Deserts, for example, rarely preserve fossils because there is little water to bury and protect remains. Mountain streams are too energetic, washing away or destroying anything that falls into them. But quiet environments, places where sediment settles gently and continuously, are ideal. Lake bottoms, river deltas, shallow seas. These are the places where fossils form, where the dead are transformed into stone, where memory is preserved. There is a particular kind of sedimentary structure called a ripple mark, and it is one of the most charming things you can find in stone. Ripple marks form when water or wind moves over sand, creating small ridges and troughs, just like the ripples you see on a beach or the bottom of a stream. When these ripples are buried and turned to stone, they are preserved, frozen in place. You can find ripple marks in rocks that are hundreds of millions of years old, and they look exactly like the ripples you might see today. It is a small, gentle connection across time, a reminder that the same forces have been shaping the Earth for as long as there has been water and sand. Mud cracks are another sedimentary structure, and they form when wet mud dries and shrinks, cracking into polygonal shapes. If the mud is then covered by new sediment before it is disturbed, the cracks are preserved. When you see mud cracks in stone, you know that the area was once exposed to air, that it dried out perhaps during a drought or a seasonal dry spell. It is a small detail, but it tells a story, a moment of heat and thirst turned to stone. Cross-bedding, which we touched on earlier, is a beautiful and informative structure. It forms when sediment is deposited at an angle, usually by wind or water. Sand dunes, for example, have a gentle slope on one side and a steep slope on the other. Sand is blown up the gentle slope and tumbles down the steep side, building up in layers that are tilted. When these dunes are buried and lithified, the tilted layers are preserved as crossbeds. By looking at the direction of the crossbeds, geologists can tell which way the wind was blowing or which way the river was flowing millions of years ago. The stone remembers the direction of ancient breezes, the path of long-vanished currents. Graded bedding is another feature, and it forms when sediment settles out of water in a particular order. Larger, heavier grains settle first, and smaller, lighter grains settle on top. The result is a layer that grades from coarse at the bottom to fine at the top. Graded bedding often forms during turbidity currents, underwater avalanches of sediment that rush down the continental slope and spread out across the ocean floor. These currents are powerful and fast, but they do not last long. When they stop, the sediment settles and a graded bed is formed. Each graded bed is the record of a single event, a single rush of sediment, a single moment of chaos that ended in stillness. Bioturbation is the disturbance of sediment by living organisms, and it is extremely common. Worms, clams, crabs, and countless other creatures burrow through mud and sand, mixing the layers, destroying the fine details of bedding. In some rocks, bioturbation is so intense that the original layering is almost completely gone, replaced by a mottled, churned texture. But even this is information. It tells us that the sediment was on the seafloor long enough for organisms to colonize it, that life was present, that the bottom was not a lifeless, anoxic desert. The traces of ancient burrows, called trace fossils, are sometimes the only evidence we have of soft-bodied creatures that left no other remains. Some rock layers are incredibly uniform, stretching for hundreds of kilometers with almost no variation. These layers formed in stable, unchanging environments, places where conditions remain the same for a very long time. Other layers are chaotic, full of jumbled fragments, pebbles mixed with mud, sudden changes in grain size. These layers tell of storms, floods, earthquakes, moments when the earth was restless and unpredictable. Both kinds of layers are important. Both tell the truth. The earth is sometimes calm and sometimes not, and the rocks record both moods with equal fidelity. There is something deeply restful about the idea that rocks are patient. They do not demand anything from us. They do not need us to understand them, though they reward us when we try. They simply exist, holding their stories, waiting. You could spend a lifetime studying a single outcrop, a single cliff face, and still find new details, new questions, new wonders. The more you look, the more you see, and there is no hurry. The rocks will still be there tomorrow, and the day after, and for millions of days beyond that. Even the hardest rock is not eternal. Wind and rain and ice slowly wear it away, grain by grain, returning it to sediment. That sediment is carried away by rivers, deposited in new places, and eventually, perhaps, turned into new rock. The cycle continues. Old mountains are worn down. New mountains rise. Rocks are broken, transported, buried, lithified, uplifted, and broken again. It is called the rock cycle, and it is one of the great rhythms of the earth, a slow dance that has been going on for billions of years and will continue for billions more. The rock cycle has no beginning and no end. It is a loop, a continuous transformation. Igneous rock, formed from molten magma, can be weathered into sediment, which becomes sedimentary rock. Sedimentary rock, buried and heated, can be transformed into metamorphic rock. Metamorphic rock, if it gets hot enough, can melt and become magma again, which cools into new igneous rock. And so it goes around and around, each type of rock becoming another, each stone passing through different forms, different lives. It is a kind of immortality, not of the individual grain, but of the substance itself. The atoms that make up a rock today have been part of countless other rocks before, and will be part of countless more in the future. When sedimentary rocks are buried deep beneath the surface, they experience increasing pressure and temperature. At first, this just causes further compaction and cementation, making the rock harder and denser. But if the conditions become extreme enough, the rock begins to change in more fundamental ways. Minerals recrystallize, new minerals form, the texture changes. This is the beginning of metamorphism, the transformation of one type of rock into another. The boundary between sedimentary and metamorphic rock is not sharp. It is a gradual transition, a slow shift from one state to another. But eventually, the rock becomes something new, something that no longer quite remembers what it was. Shale, when metamorphosed, becomes slate. Slate is harder, denser, and it splits into smooth, flat sheets. It has been used for roofing tiles and chalkboards for centuries. With more heat and pressure, slate becomes phyllite, which has a slight sheen from tiny mica crystals. Phyllite, in turn, can become schist, which has larger crystals and a more pronounced foliation, a layered texture. And schist, under the most extreme conditions, can become gneiss, a rock with bold, striped patterns of light and dark minerals. Each step in this progression represents deeper burial, higher temperatures, more intense pressure. The rock is being cooked, slowly, deep in the Earth's crust, transformed by forces we can barely imagine. Limestone, when metamorphosed, becomes marble. Marble is prized for its beauty, its smooth texture, its ability to take a high polish. It has been used in sculpture and architecture for thousands of years. The Parthenon in Athens, Michelangelo's David, countless monuments and buildings, all carved from marble, from stone that was once the shells of tiny sea creatures, pressed and heated and transformed into something new. Marble is metamorphic, but it still contains the calcium carbonate of its sedimentary parent. It is a bridge between two worlds, a reminder that transformation does not erase the past, but builds upon it. Sandstone, when metamorphosed, becomes quartzite. Quartzite is one of the hardest rocks on Earth because it is made almost entirely of interlocking quartz crystals. It is difficult to break, resistant to weathering, and it can form dramatic, rugged landscapes. The quartzite cliffs and ridges stand tall, outlasting softer rocks around them, a testament to the strength that comes from deep transformation. Metamorphic rocks often have a foliated texture, meaning they have a layered or banded appearance. This foliation forms because minerals align themselves perpendicular to the direction of pressure. Imagine squeezing a deck of cards. The cards align, all facing the same way. Minerals in metamorphic rock do something similar. Mica, for example, forms flat, sheet-like crystals, and under pressure, these sheets align, giving the rock a layered look. Not all metamorphic rocks are foliated, though. Marble and quartzite, for example, are non-foliated. Their minerals do not align in layers, so the rock has a more uniform texture. The study of metamorphic rocks can tell us about the conditions deep within the earth. By examining the minerals in a metamorphic rock, geologists can estimate the temperature and pressure it experienced. Different minerals form at different conditions, and the combination of minerals in a rock is like a thermometer and pressure gauge, recording the environment in which the rock was transformed. This allows us to map the thermal structure of ancient mountain belts, to understand how continents collide and how mountains are built. It is detective work, piecing together the past from the clues left in stone. But tonight, our focus is on the sedimentary, on the layers that form slowly, quietly, at the surface or just beneath it. These are the rocks that are easiest to see, easiest to touch, and in many ways, easiest to understand. They form in environments we recognize: rivers, lakes, oceans, deserts. They contain fossils of creatures that once lived. They tell stories we can follow, step by step, layer by layer. They're the Earth's diary, written in a language that, with patience, we can learn to read. And there is something so calming about that. The idea that the Earth keeps a record, that nothing is truly lost. Every storm, every season, every slow shift in climate leaves a trace. The rocks remember, even if we do not. They hold the memory of ancient forests, of seas that sparkled under different stars, of deserts where no human ever walked. And they hold it all without judgment, without preference. They simply are. The Grand Canyon reveals its layered story not just through depth, but through color. Each band of rock carries a different hue, a different mineral signature, a different moment in time. The red wall limestone glows warm in afternoon light, its iron-rich surface telling of ancient tropical seas. Below it, the bright angel shale holds softer greens and purples, mudstones that once settled in quieter waters. These colors are not decoration. They are chemistry made visible, the presence of iron, manganese, organic matter, each element leaving its gentle mark across millions of years. Geologists read these color bands like pages in a book, and you can too, even from a distance. A red layer often speaks of iron oxide, rust formed in the presence of oxygen, suggesting the rock spent time exposed to air or oxygen-rich water. Gray and black layers may hold organic carbon, the remains of life that decomposed in low oxygen conditions, preserving its dark signature. Green hues can indicate the presence of minerals like chlorite or glauconite, formed in specific marine environments. Every color is a clue, a whisper from the past about the conditions that existed when that layer formed. And these layers do not exist in isolation. They stack upon one another in sequences that reveal the rise and fall of ancient seas, the advance and retreat of deserts, the slow dance of climate over deep time. When sea levels rose, marine sediments spread across the land, depositing limestone and shale. When seas withdrew, rivers and winds took over, laying down sandstone and silt. This rhythm of deposition created the alternating bands we see today, each transition marking a shift in Earth's environmental story. Some of these transitions are sharp, almost knife-edge clean. These are called unconformities, and they represent gaps in the geological record, moments when erosion stripped away layers or when deposition simply paused for millions of years. An unconformity is a missing chapter, a silence in the stone. Yet even silence tells a story. It speaks of uplift, of landscapes rising into the air where wind and water could wear them down, of time passing without leaving a trace. Geologists treasure these gaps as much as the layers themselves, because they reveal the dynamic nature of Earth's surface, always shifting, always responding to forces deep below and high above. One of the most famous unconformities lies at the base of the Tepete sandstone in the Grand Canyon, where it rests directly upon ancient Precambrian rocks. Between these two layers lies a gap of over 1 billion years, a span of time so vast it challenges comprehension. The older rocks below were once mountains, worn down to their roots over eons. The younger sandstone above represents a sea that eventually covered this ancient, flattened landscape. Standing at this boundary, you are touching two worlds separated by more time than the entire span of complex life on Earth. Unconformities come in different forms, each with its own quiet character. A disconformity occurs when layers above and below are parallel, but time is missing between them, as if pages were torn from a book without disturbing the binding. An angular unconformity shows tilted or folded layers below, cut flat by erosion, then covered by new horizontal layers above. This speaks of dramatic events. The older layers were deposited, then compressed and tilted by tectonic forces, then eroded flat, then buried again. All of this takes tens or hundreds of millions of years. Yet the boundary itself may be no thicker than a knife blade. A nonconformity is perhaps the most striking. Sedimentary layers resting directly upon igneous or metamorphic rock. This represents the deepest kind of time gap, where the roots of ancient mountains meet the sediments of much younger seas. The contrast is stark: crystalline granite or schist below, soft sandstone or limestone above. Each side of this boundary formed in utterly different ways, under different conditions. Yet here they lie together, pressed into the same cliff face, the same canyon wall. Moving beyond unconformities, let us consider the quiet phenomenon of graded bedding. In certain layers, you can see a gradual change from coarse particles at the bottom to fine particles at the top. This happens when a sudden influx of sediment, perhaps from a turbidity current underwater or a flood on land, deposits material all at once. The heaviest grains settle first, then progressively lighter ones, creating a smooth gradation from bottom to top. Each graded bed represents a single event, a moment of energy followed by settling calm. Stacks of graded beds tell of repeated pulses, storms, or underwater avalanches happening again and again over time. Turbidity currents themselves are fascinating, quiet catastrophes of the deep ocean. They occur when sediment on a continental slope becomes unstable and flows downward as an underwater avalanche, a dense cloud of mud and sand moving across the ocean floor. These currents can travel for hundreds of miles, spreading sediment across vast abyssal plains. When they finally slow and stop, they deposit graded beds called turbidites. These layers are common in deep marine sediments, and they reveal the hidden violence of the ocean depths, events that happen in darkness, far from any shore, yet leave their mark in stone. On land, rivers create their own distinctive layering patterns. Floodplains accumulate fine silts and clays during floods, while river channels deposit coarser sands and gravels. Over time, as a river meanders and shifts its course, it leaves behind a complex three-dimensional puzzle of sediment types. Geologists can reconstruct ancient river systems by studying these patterns, tracing the path of waterways that flowed millions of years ago. The rock remembers the river's shape, its energy, its seasonal rhythms. Deltas, where rivers meet the sea, create especially intricate layering. The river slows as it enters standing water, dropping its sediment load in a predictable sequence. Coarse material settles first, near the river mouth, building forward into the sea. Finer material is carried farther out, settling in deeper, quieter water. The result is a set of angled layers, called foreset beds, that slope gently seaward. Above them lie flat top-set beds, deposited on the delta's surface. Below lie bottom-set beds, the finest muds that settled in the deepest water. This three-part structure is the signature of a delta, preserved in stone long after the river has vanished. Ancient deltas are economically important because they often contain oil and gas. Organic matter trapped in delta sediments can, under the right conditions of heat and pressure, transform into hydrocarbons. The layered structure of deltas also creates natural traps where oil and gas can accumulate, held in place by impermeable layers above. Much of the world's petroleum comes from ancient deltaic deposits, energy stored in stone for hundreds of millions of years, now extracted and burned in a geological instant. But let us return to the surface, to the visible beauty of layered rock. In many places, erosion has carved these layers into steps and ledges, creating natural staircases in the landscape. Harder, more resistant layers form cliffs and overhangs, while softer layers erode back into slopes and benches. This differential erosion reveals the varying strength of different rock types. A limestone layer might stand as a bold cliff, while a shale layer beneath it crumbles into a gentle slope. The landscape becomes a three-dimensional expression of the rock's properties, each layer asserting its character through the way it weathers and breaks. In desert regions, this steppe topography is especially pronounced. Lack of vegetation means that every detail of the rock is exposed, every layer visible. The clarity is breathtaking. You can trace a single layer for miles, watching it rise and fall with the tilt of the land, sometimes disappearing underground, sometimes standing proud in a cliff face. The continuity of these layers across vast distances is humbling. A single bed of sandstone might extend for hundreds of miles, representing a moment in time when sand covered an entire region, all of it now frozen in stone. These extensive layers are called formations, and geologists have named them, mapped them, studied their extent and characteristics. The Navajo sandstone, for example, covers much of the American Southwest, a thick deposit of ancient desert dunes now turned to stone. The Kaibab limestone caps the rim of the Grand Canyon, a marine layer that once lay beneath a shallow tropical sea. Each formation has a type locality, a place where it is especially well exposed and where its characteristics were first described. These names become familiar to anyone who spends time with the rocks, like the names of old friends. Formations are grouped into larger units called groups and subdivided into smaller units called members and beds. This hierarchy allows geologists to organize and communicate about the immense complexity of the rock record. It is a language, a way of speaking precisely about layers that may look similar but differ in age, composition, or origin. Learning this language takes time, but it opens up the landscape in new ways, turning a jumble of cliffs and slopes into a readable history. Within formations, geologists also recognize facies, which are variations in rock type that occur across the same time interval. Imagine an ancient shoreline. At the same moment in time, sand is being deposited on the beach, mud in the lagoon behind it, and limestone in the open ocean beyond. These different sediment types are all forming simultaneously, but in different environments. As sea level changes or the shoreline migrates, these facies shift position, creating complex three-dimensional patterns in the rock. Understanding facies is key to reconstructing ancient environments, to seeing not just what was deposited, but where and why. One particularly beautiful example of facies change is the transition from reef to lagoon to open ocean in ancient carbonate platforms. The reef itself is a framework of coral, algae, and other organisms, now preserved as a massive, chaotic limestone. Behind the reef, in the protected lagoon, fine carbonate mud settled, forming smooth, even layers. In front of the reef, in deeper water, the limestone is darker, richer in organic matter, deposited in the quiet depths. Each facies has its own texture, its own fossil assemblage, its own story. Together, they paint a picture of a living, breathing, ancient ecosystem. Fossils themselves are perhaps the most captivating feature of sedimentary layers. They are life turned to stone, the shapes and structures of organisms preserved across unimaginable spans of time. A fossil is not usually the original material of the organism. Most often, the organic matter has been replaced, molecule by molecule, with minerals like calcite, silica, or pyrite. This process, called permineralization, happens slowly as mineral-rich water percolates through the sediment. The original structure is preserved in exquisite detail, even down to the cellular level in some cases. Some fossils are simply impressions, molds left in the sediment when the organism decayed. Others are casts, formed when sediment filled the mold and hardened. Trace fossils, also called ichnofossils, preserve not the organism itself, but evidence of its activity. Footprints, burrows, feeding traces. These are especially valuable because they reveal behavior, showing how ancient creatures moved, fed, and interacted with their environment. A trail of footprints across a mudstone layer is a moment of motion frozen in time, the path of an animal that lived and died millions of years ago. The distribution of fossils and rock layers follows clear patterns, and these patterns are the foundation of biostratigraphy, the use of fossils to date and correlate rock layers. Certain species existed only during specific intervals of geological time. When you find their fossils, you know the age of the rock. These are called index fossils, and they are invaluable for matching up layers from different locations. A layer containing a particular species of trilobite in Nevada can be correlated with a layer containing the same species in China, even though the rocks may look different. The fossil provides the link, the common thread of time. This principle allowed geologists, long before radiometric dating, to construct the geological time scale. By carefully observing which fossils appeared in which layers, and in what order, they built a relative chronology of Earth history. They recognized that life had changed over time, that certain groups of organisms appeared, flourished, and went extinct, replaced by others. The rock layers, with their fossils, told this story of change, of evolution, of the unfolding diversity of life. The geological timescale is divided into eons, eras, periods, and epochs, each defined by changes in the fossil record. The boundaries between these divisions often mark mass extinctions, moments when a significant percentage of species disappeared. The end of the Cretaceous period, marked by the extinction of the non-avian dinosaurs, is one such boundary. It is visible in the rock as a thin layer of clay enriched in iridium, an element rare on Earth's surface but common in asteroids. This layer, found worldwide, is evidence of the impact that triggered the extinction, a catastrophic event recorded in a band of sediment just a few centimeters thick. But most of the rock record is not catastrophic. It is the accumulation of ordinary moments, the quiet settling of sediment day after day, year after year, millennium after millennium. This is the deep comfort of sedimentary rocks. They are patient. They do not rush. They record the everyday as faithfully as the extraordinary. A mudstone formed from the slow settling of silt in a lake is just as much a part of Earth's history as a layer marking a volcanic eruption or an asteroid impact. Every layer matters. Every grain has its place. Consider the formation of coal, a sedimentary rock composed almost entirely of plant material. Coal forms in swamps and bogs, places where dead vegetation accumulates faster than it can decay. Over time, this organic matter is buried under more sediment. The weight and heat of burial drive off water and volatile compounds, concentrating the carbon. Peat becomes lignite. Lignite becomes bituminous coal. And with enough heat and pressure, bituminous coal becomes anthracite. Each stage represents a deeper burial, a longer time, a greater transformation. The plants that grew in ancient swamps hundreds of millions of years ago are now the coal we burn for energy, their stored sunlight released as heat and light. Coal seams are often interbedded with other sedimentary rocks, shales and sandstones that represent times when the swamp was flooded by a river or the sea. These cyclical deposits, called cyclothems, reveal the rhythm of sea level change and climate fluctuation in the past. A single coal seam might represent thousands of years of plant growth, while the layers above and below it represent brief floods or marine incursions. Reading these cycles is like listening to a slow, deep heartbeat of the earth, the pulse of environmental change over deep time. Evaporites are another special type of sedimentary rock, formed when water evaporates and leaves behind dissolved minerals. This happens in arid environments, in shallow seas or isolated lakes where evaporation exceeds inflow. The minerals precipitate in a predictable sequence as the water becomes more and more concentrated. Calcite forms first, then gypsum, then halite, rock salt, and finally more exotic salts like sylvite and carnallite. Thick deposits of evaporites indicate prolonged periods of aridity and restricted water circulation. They are common in the geological record, evidence that Earth's climate has fluctuated between wet and dry many times. Halite, or rock salt, is especially interesting. It forms perfect cubic crystals, and in thick deposits, it can flow like a very slow fluid under pressure. This creates salt domes, massive structures that rise through overlying rock layers, deforming them as they ascend. Salt domes are important in petroleum geology, because they create traps where oil and gas can accumulate. They also bring deep layers closer to the surface, making them easier to study. Some salt deposits are mined for table salt, others for road salt, and still others are used to create underground storage caverns for natural gas or petroleum. Gypsum, another evaporite mineral, is soft and often forms beautiful crystals. It is used to make plaster of Paris and drywall. Large deposits of gypsum, like those in the white sands of New Mexico, create surreal landscapes of white dunes and glittering expanses. The gypsum there is constantly being eroded from ancient lake beds, blown into dunes, then dissolved and redeposited. It is a landscape in flux, yet rooted in ancient evaporite layers. Chert, also called flint, is a hard, fine-grained sedimentary rock composed of microcrystalline quartz. It often forms as nodules within limestone or as distinct layers. Chert can form from the accumulation of silica-rich organisms like diatoms and radiolarians, or from the precipitation of silica from water. It is extremely hard and breaks with a conchoidal fracture, creating sharp edges. For this reason, chert was prized by ancient peoples for making tools and weapons. A chert nodule, weathered out of a limestone layer, could be flaked into a knife or arrowhead, a piece of the rock record repurposed for human use. Banded iron formations are among the oldest and most mysterious sedimentary rocks. They consist of alternating layers of iron-rich minerals and chert, often with striking red, black, and silver bands. These formations are found in rocks older than about 2 billion years, and they represent a time when Earth's oceans contained dissolved iron. The iron precipitated out, possibly due to the activity of early photosynthetic organisms that produced oxygen. This oxygen reacted with the iron, causing it to settle to the seafloor as iron oxide. The banding may represent seasonal or cyclical changes in oxygen production or ocean chemistry. Banded iron formations are not just beautiful. They are a record of the oxygenation of Earth's atmosphere, one of the most important events in our planet's history. These ancient rocks also contain most of the world's iron ore. The iron that builds our cities, our cars, our infrastructure, comes from layers deposited billions of years ago by processes we are still working to fully understand. It is humbling to think that the steel in a bridge or a skyscraper was once dissolved in an ancient ocean, precipitated by microbial activity, buried and compressed, then uplifted and mined, transformed by human hands into something new. Phosphorites are sedimentary rocks rich in phosphate minerals. They form in areas of upwelling, where deep, nutrient-rich ocean water rises to the surface, supporting abundant marine life. When these organisms die, their remains accumulate on the seafloor, concentrating phosphorus. Over time, this becomes a phosphorite layer. These rocks are mined for fertilizer, because phosphorus is essential for plant growth. The phosphorus in the food you eat may have come from a layer deposited millions of years ago in an ancient sea, now spread across fields to nourish crops. Diatomite, also called diatomaceous earth, is composed of the silica shells of diatoms, microscopic algae that lived in lakes and oceans. When they died, their shells accumulated in vast numbers, forming thick deposits. Diatomite is light, porous, and has many uses. As a filter medium, as an absorbent, in toothpaste, in insulation. It is soft enough to crumble between your fingers, yet each grain is a tiny, intricate shell, a work of natural architecture on a microscopic scale. Limestone, which we have mentioned before, deserves deeper attention. It is one of the most common sedimentary rocks, and it forms in many ways. Most limestone is biological in origin, composed of the shells and skeletons of marine organisms. Corals, mollusks, foraminifera, coccolithophores all contribute their calcium carbonate structures to the seafloor. Over time, these accumulate and lithify into limestone. Some limestone forms directly from the precipitation of calcium carbonate from seawater, especially in warm, shallow seas. This can create oolitic limestone, made of tiny spherical grains called ooids, each formed by the concentric precipitation of calcite around nucleus. Limestone is soluble in weak acids, including the carbonic acid formed when rainwater absorbs carbon dioxide from the atmosphere. This means that limestone landscapes are prone to chemical weathering, creating karst topography. Karst features include sinkholes, caves, underground rivers, and disappearing streams. Water seeps into cracks and joints in the limestone, slowly dissolving the rock and enlarging the openings. Over thousands of years, this creates vast cave systems, some extending for miles underground. Inside these caves, the dissolved calcium carbonate can precipitate again, forming speleothems, stalactites, stalagmites, flowstone, draperies. Water dripping from the cave ceiling leaves behind a tiny amount of calcite with each drop. Over centuries, this builds downward into a stalactite. Where the water drips onto the floor, it builds upward into a stalagmite. Sometimes they meet, forming a column. The growth is incredibly slow, often just a fraction of a millimeter per year, but the results are breathtaking, delicate formations that seem almost alive in their complexity. These cave formations are layered too, on a microscopic scale. Each layer represents a period of deposition, and the layers can preserve information about past climate. The chemistry of the calcite, the ratios of certain isotopes, can reveal temperature and rainfall patterns from thousands of years ago. Scientists drill cores from stalagmites and read them like tree rings, reconstructing ancient climates with remarkable precision. The cave, hidden from the surface, becomes a library of environmental history. Returning to the surface, let us consider the role of weathering in creating sediment. Weathering is the breakdown of rock at or near Earth's surface, and it comes in two main types: physical and chemical. Physical weathering breaks rock into smaller pieces without changing its chemical composition. Frost wedging, where water freezes in cracks and expands, is a common form. The expansion exerts tremendous force, splitting the rock. This happens over and over, winter after winter, gradually breaking solid rock into rubble. Chemical weathering alters the minerals in the rock, transforming them into new minerals or dissolving them entirely. Water is the main agent, especially when it is slightly acidic. Feldspar, a common mineral in granite, weathers to clay minerals. This is why granite landscapes often have a thick layer of clay-rich soil. The quartz in granite, being more resistant, remains as sand grains. Over time, the granite crumbles into a mixture of clay and sand, which can then be transported and deposited elsewhere, becoming shale and sandstone. The rate of weathering depends on climate. Warm, wet climates promote chemical weathering because chemical reactions proceed faster at higher temperatures and require water. Cold, dry climates favor physical weathering, especially frost wedging. This is why tropical regions often have deep, clay-rich soils, while polar and desert regions have thinner soils and more physical breakdown of rock. Plants also play a role in weathering. Their roots grow into cracks, exerting pressure and breaking rock apart. They also release organic acids that enhance chemical weathering. Lichens, some of the first organisms to colonize bare rock, secrete acids that slowly dissolve minerals, beginning the process of soil formation. Over time, what was once solid rock becomes a medium for life, a layer of soil that supports plants, which in turn accelerate weathering. It is a feedback loop, a partnership between life and stone. Once weathered, sediment must be transported before it can become a new rock. Wind, water, ice, and gravity all move sediment from one place to another. Rivers are the most important agents of sediment transport on land. They carry dissolved minerals, fine clays and silts in suspension, and coarser sands and gravels along their beds. The energy of the river determines what it can carry. A fast-flowing mountain stream can move boulders. A slow, meandering river can only carry silt and clay. When the river slows, it drops its load, depositing sediment in predictable patterns. Glaciers are also powerful transporters of sediment. They pluck rock from the bedrock beneath them and carry it along, embedded in the ice. When the glacier melts, it deposits this material as till, an unsorted mixture of clay, sand, gravel, and boulders. Glacial deposits are distinctive because of this lack of sorting. A single layer of till can contain particles ranging from clay-sized to house-sized, all jumbled together. This is very different from water-deposited sediments, which are sorted by size. Wind can transport only fine particles, sands and silts. It creates dunes, which have their own internal layering, crossbeds that record the direction of the wind. Ancient dune deposits, now turned to sandstone, preserve these crossbeds, allowing geologists to reconstruct wind patterns from millions of years ago. The Navajo sandstone, mentioned earlier, is full of sweeping crossbeds, evidence of vast deserts where winds piled sand into dunes hundreds of feet high. Gravity moves sediment downslope in landslides, rockfalls, and slower processes like soil creep. These mass movements are especially important in mountainous terrain. They deliver sediment from high elevations to valley floors, where rivers can pick it up and carry it farther. Every rockfall, every avalanche, is a small step in the long journey of sediment from mountain to sea. The ultimate destination for most sediment is the ocean. Rivers carry it to the coast, where it is deposited in deltas, estuaries, and along the shoreline. Waves and currents redistribute it, moving along the coast or carrying it out to deeper water. Eventually, it settles on the seafloor, layer upon layer, beginning the long process of lithification. The ocean floor is a vast repository of sediment, accumulating at rates measured in millimeters or centimeters per thousand years. It is patient work, the building of future continents, the creation of rocks that will one day be uplifted and exposed. Not all sediment reaches the ocean. Some is trapped in lakes, in deserts, in valleys. These deposits are important too, because they record local conditions, local climates, and ecosystems. A lake bed can preserve a detailed record of the surrounding environment, with layers that represent individual years or even seasons. Varves are annual layers in lake sediments, formed when coarse material settles in summer and fine material in winter. Counting varves is like counting tree rings, a way to measure time in the recent geological past. In some places, sediment accumulates so rapidly that it buries organisms before they can decay, creating exceptional fossil preservation. These sites, called Lagerstätten, are windows into ancient life. The Burgess Shale in Canada, the Solnhofen limestone in Germany, the Green River Formation in the United States, all are Lagerstätten, famous for their exquisitely preserved fossils. Soft tissues, which normally decay quickly, are preserved as films of carbon or replaced by minerals. These fossils reveal details of anatomy and ecology that are invisible in ordinary fossils, showing us ancient life in stunning clarity. The Green River Formation, for example, contains beautifully preserved fish, insects, plants, and even feathers. It formed in a series of large lakes that existed in Wyoming, Colorado, and Utah about 50 million years ago. The lakes were stratified, with oxygen-poor bottom waters that prevented scavengers and bacteria from destroying dead organisms. When a fish died and sank to the bottom, it was buried quickly in fine mud, and its body was preserved in remarkable detail. Today, these fossils are prized by collectors and scientists alike, each one a snapshot of life in an ancient lake. The preservation of fossils depends on many factors: the type of organism, the environment of deposition, the chemistry of the sediment, the speed of burial. Hard parts like shells and bones are more likely to be preserved than soft tissues. Organisms that live in environments where sediment accumulates rapidly, like river deltas or shallow seas, are more likely to be fossilized than those in environments with slow deposition or high energy, like mountain streams or rocky shorelines. The fossil record is therefore biased towards certain types of organisms and environments, and paleontologists must account for these biases when interpreting ancient life. Despite these biases, the fossil record is astonishingly rich. Millions of fossils have been collected and studied, representing thousands of extinct species. Each one adds to our understanding of the history of life, the patterns of evolution, the responses of organisms to environmental change. Fossils are not just curiosities. They are data, evidence of how life has changed over billions of years, how it has adapted, diversified, and sometimes failed. And the layers that contain these fossils are themselves evidence of Earth's dynamic history. They show us that the planet is not static, that continents move, climates change, seas rise and fall. The rock record is a record of change, of processes that operate on timescales far beyond human experience. Yet we can read this record, we can decipher its language, and in doing so, we connect with deep time, with a vast sweep of Earth's history. This connection is part of the comfort of geology. It places us in context, shows us that we are part of a much larger story. The rocks beneath our feet are ancient, patient, enduring. They have witnessed the rise and fall of mountains, the coming and going of seas, the evolution and extinction of countless species. They will be here long after we are gone, continuing to record, continuing to tell their story to anyone who takes the time to listen. The journey through stone continues now into deeper, quieter territories, where rock layers reveal not only their own stories, but the grand movements of the earth itself. We have wandered through sediment and color, through fossils and ancient waters, and now we turn our attention to the forces that bend, break, and reshape these patient layers over time. The stones remain calm through it all, recording every shift with silent precision. When layers of rock are subjected to pressure from the sides, they do not always break. Sometimes they bend. This bending creates folds, gentle or dramatic curves in what were once flat beds of sediment. Imagine a stack of blankets pushed slowly from both ends. They wrinkle and arch. Rock does the same, though over millions of years. The tops of these folds are called anticlines, and the valleys between them are synclines. Walking through folded mountains, you can see layers tilted at steep angles, sometimes even vertical, testifying to the immense but gradual forces that shape them. The patience of stone allows it to flow, in its own slow way, under enough pressure and time. Folds tell us about the direction and intensity of ancient tectonic forces. When continents collide, the crust crumples, and sedimentary layers that formed peacefully on ancient sea floors are lifted high into mountain ranges. The Appalachians, the Alps, the Himalayas, all contain folded rock layers, each curve a frozen wave of Earth's restless energy. Geologists can read these folds like sentences, understanding which direction the pressure came from, how intense it was, and when it happened. The stones remember, even when the forces that shape them have long since quieted. Sometimes, instead of bending, rock layers break. These breaks are called faults. A fault is a fracture in the Earth's crust along which movement has occurred. The rock on one side shifts relative to the other, sometimes by centimeters, sometimes by kilometers. Faults can be gentle or violent, slow or sudden. They are the seams where the Earth's crust adjusts to stress. There are many types, each with its own character. Normal faults occur when the crust is being pulled apart, allowing one block to slide down relative to another. Reverse faults happen when the crust is compressed, pushing one block up over another. Strike-slip faults involve horizontal movement, where blocks slide past each other sideways. Each type leaves a distinct signature in the rock layers. The presence of a fault can sometimes be seen directly, a sharp line cutting through otherwise continuous layers. Other times, the evidence is more subtle, layers that do not quite match up on either side, or a zone of crushed and fractured rock called a fault zone. Faults are not just geological curiosities. They are also the pathways along which earthquakes occur. When stress builds up along a fault, the rocks eventually slip, releasing energy in the form of seismic waves. But even in their violence, faults are part of the Earth's slow, ongoing conversation with itself, a necessary adjustment in the patient architecture of stone. Faults can also create gaps in the geological record, similar to unconformities. If a fault moves after layers have formed, it can juxtapose rocks of very different ages right next to each other. Geologists must carefully reconstruct the original positions of layers to understand the full story. This detective work, piecing together the puzzle of displaced stone, is one of the quiet joys of geology. Each fault is a chapter, sometimes missing pages, but always meaningful. In some places, rock layers are not just tilted or broken, but completely overturned. Intense folding can cause layers to flip upside down, so that older rocks lie on top of younger ones, defying the usual order. These overturned folds, called recumbent folds, are rare and dramatic. They require extraordinary forces and deep burial. When geologists encounter them, they must look closely at sedimentary structures, like cross-bedding or graded bedding, to determine which way was originally up. The stones, even when turned on their heads, still carry the clues needed to read them correctly. Another fascinating feature found in rock layers is the presence of joints. Joints are fractures in rock where no significant movement has occurred, Unlike faults, they form when rock is subjected to stress, but instead of sliding, it simply cracks. Joints often form in regular patterns, creating sets of parallel fractures. In sedimentary rocks, joints can develop as the rock is uplifted and the pressure from overlying layers is removed, allowing the rock to expand and crack. Joints are important because they influence how water moves through rock, how cliffs erode, and even how ancient peoples quarried stone for building. The straight edges of many stone blocks and old structures follow natural joint planes, where the rock was easiest to split. Columnar jointing is a particularly beautiful type of fracture pattern, though it occurs more commonly in volcanic rocks than sedimentary ones. When lava cools, it contracts, and the contraction creates polygonal columns, often hexagonal, that stand like a forest of stone pillars. While less common in sedimentary rocks, similar patterns can occasionally form in certain conditions, and they remind us that stone, in cooling or drying or shifting, seeks geometric harmony. There is a quiet order, even in fracture. Rock layers also preserve evidence of ancient climates. Certain types of sedimentary rocks form only under specific climatic conditions. Evaporites, for example, indicate arid climates where evaporation exceeded precipitation. Thick coal seams suggest warm, wet conditions with lush vegetation. Glacial deposits, called tillites, are unsorted mixtures of sediment left behind by melting ice sheets, indicating cold climates. By studying the types of sedimentary rocks in a sequence, geologists can reconstruct how climate changed over time in a particular region. The stones are climate archives, holding records of droughts and floods, ice ages, and tropical warmth. One of the most striking climate indicators in rock layers is the presence of drop stones. These are larger rocks found within fine-grained sediments like mud or silt, seemingly out of place. They were carried by icebergs and dropped into the ocean or lake as the ice melted. The fine sediments settled slowly from the water, while the large stone fell suddenly from above. Drop stones are direct evidence of ancient glaciers and cold climates, little messengers from frozen times, now resting quietly in stone. Sedimentary rocks also record changes in sea level. When sea level rises, the shoreline moves inland, and marine sediments are deposited over what were once coastal or terrestrial environments. This creates a transgressive sequence where deeper water sediments overlie shallower water sediments. When sea level falls, the opposite occurs, creating a regressive sequence. These shifts are recorded in the types of rocks and fossils found in successive layers. Sea level has risen and fallen many times throughout Earth's history, driven by the growth and melting of ice sheets, the changing volume of ocean basins, and the shifting of tectonic plates. Each rise and fall is written in the layers, a gentle tide of stone. The concept of sequence stratigraphy takes this idea further, dividing rock layers into packages bounded by surfaces that represent significant changes in sea level or sediment supply. These sequences can be traced across large regions, sometimes across entire continents, allowing geologists to correlate rock layers over vast distances. It is a way of seeing the big picture, understanding how local layers fit into global patterns. The stones speak not just of one place, but of the whole Earth's rhythm. Rock layers also contain evidence of ancient life beyond fossils. Trace fossils, or ichnofossils, are the preserved marks of biological activity. Footprints, burrows, feeding trails, and nests. These traces tell us how ancient organisms behaved, where they lived, and how they interacted with their environment. A burrow in sandstone shows that a creature once lived there, even if the creature itself did not fossilize. Trace fossils are especially valuable because they are preserved in place, showing exactly where the activity occurred. They add a layer of life and movement to the silent stone. Some trace fossils are so distinctive that they're given their own names, like skelethos, vertical burrows made by worm-like creatures in sandy sediments, or cruziana, the crawling traces of trilobites. These traces are often more common than body fossils and can be found in rocks where body fossils are rare. They are the footprints of deep time, quiet evidence of lives lived and forgotten, now held gently in the rock. Bioturbation is the mixing of sediment by living organisms, and it is visible in many sedimentary rocks. Creatures burrow, dig, and churn the sediment, disrupting the original layering. In some rocks, bioturbation is so intense that the original layers are completely homogenized, creating a mottled texture. In others, burrows stand out as distinct shapes against the surrounding rock. Bioturbation is a sign of a healthy, active ecosystem on the ancient seafloor or lake bed. It shows that life was present, busy, and abundant. The stones remember not just the organisms, but their restless energy. Rock layers also preserve rare and unusual events. Volcanic ash falls, for example, can blanket large areas in a short time, creating thin, distinctive layers within sedimentary sequences. These ash layers, called bentonite when altered to clay, are incredibly useful for dating and correlating rock layers because they represent a single moment in time. A volcanic eruption might last days or weeks, but geologically, that is an instant. The ash settles, and the layer it forms is like a time marker, a line drawn across the landscape that can be traced for hundreds of kilometers. It is a snapshot, a frozen moment in the slow unfolding of stone. Impact layers are even rarer. When a large meteorite strikes the Earth, it creates a layer of debris that can be spread over vast areas. The most famous is the thin layer of iridium-rich clay found at the boundary between the Cretaceous and Paleogene periods, marking the impact that contributed to the extinction of the dinosaurs. This layer is found all over the world, a quiet testament to a catastrophic moment. The stones hold even the sky's violence, softly, patiently, without judgment. Some rock layers contain concretions, which are hard, often spherical masses that form within sedimentary rock. They grow around a nucleus, such as a fossil or a grain, as minerals precipitate from groundwater. Concretions can be small as marbles or large as boulders. They are often more resistant to erosion than the surrounding rock, so they weather out and litter the landscape. Breaking open a concretion sometimes reveals a beautifully preserved fossil inside, protected by the hard shell. Concretions are like nature's time capsules, holding secrets within their stony hearts. Geodes are similar but hollow, lined with crystals that grew inward from the walls. They form in cavities within rock, often in limestone or volcanic rock. The crystals, usually quartz or calcite, grow slowly over thousands or millions of years, filling the space with sparkling beauty. Finding a geode is a small joy, a hidden treasure within plain stone. They remind us that even within the most ordinary rock, there can be unexpected wonder. Rock layers also record the movement of groundwater. Water flowing through porous rock can dissolve minerals and redeposit them elsewhere, creating features like vugs, small cavities lined with crystals, or cement that binds grains together more tightly in certain zones. Groundwater can also create color bands by depositing iron or manganese oxides. These bands, called Lees-Gang rings, form rhythmic patterns that look almost painted. They are the result of chemical reactions as minerals diffuse through the rock, a slow, quiet artistry of water and stone. In some places, groundwater dissolves limestone to create caves. Over time, these caves can collapse, and the overlying rock layers subside into the void, creating a feature called a sinkhole or a collapsed structure. In the rock record, these appear as disrupted layers, chaotic zones where the orderly sequence is interrupted. They are evidence of hidden spaces, of water's patient work deep underground, and of the occasional sudden surrender of stone to gravity. Rock layers also interact with the surface world in gentle ways. Soil forms from the weathering of rock, a slow transformation from stone to life-supporting material. The type of rock influences the type of soil. Limestone weathers to produce alkaline soils, while granite weathers to produce more acidic soils. Shale, rich in clay, produces heavy, sticky soils. Sandstone produces sandy, well-drained soils. The plants that grow, the animals that live, the agriculture that humans practice, all are influenced by the rocks beneath. The stones shape the living world, quietly, from below. Sedimentary rocks are also economically important. Coal, oil, and natural gas are all found in sedimentary rocks. Coal forms from ancient plant material, oil and gas from ancient marine organisms. These fossil fuels are the compressed, transformed remains of life, stored in stone for millions of years. Sedimentary rocks also host valuable minerals like uranium, copper, and phosphate. Building stones like limestone and sandstone have been quarried for millennia. The stones not only tell stories, they also provide resources. They build our cities, they warm our homes. They are both archive and material, both past and present. Phosphate rock, or phosphorite, forms in certain marine environments where upwelling brings nutrient-rich water to the surface. The phosphate accumulates in layers and is later mined for use in fertilizers. Without phosphate, modern agriculture would struggle to feed the world. This humble sedimentary rock, formed in ancient seas, is now essential to human survival. The stones give quietly and generously. Rock layers also preserve evidence of ancient ecosystems. A single layer might contain fossils of many different species, all living together at the same time. By studying these assemblages, paleontologists can reconstruct entire ecosystems. What ate what, who lived where, how energy flowed through the community. These reconstructions are like windows into lost worlds, vivid and detailed despite being millions of years old. The stones hold not just individual lives, but entire webs of life, frozen in time. Some rock layers contain evidence of mass extinctions, moments when large percentages of species disappeared in a geologically short time. These layers often show a sudden change in fossil diversity, with many species present below the layer and absent above it. Mass extinctions are sobering reminders of life's fragility, but also of its resilience. After each extinction, life recovered, diversified, and filled the world again. The stones record both the loss and the renewal, the endings and the beginnings. Rock layers also show evidence of evolutionary change. Fossils in lower layers are often simpler and more primitive than those in higher layers. Over time, organisms became more complex, more diverse, more specialized. This pattern is consistent across the world and is one of the strongest pieces of evidence for evolution. The stones are evolution's library, each layer a page in the long story of life's development. The changes are slow, incremental, but unmistakable. The stones do not argue or debate, they simply show what was. In some places, rock layers are exposed in cliffs or canyon walls, creating natural cross-sections through time. The Grand Canyon is perhaps the most famous example, where the Colorado River has cut through nearly 2 billion years of rock, exposing layer after layer in a stunning display. Walking down into the canyon is like walking backward through time, each step taking you deeper into Earth's history. The oldest rocks at the bottom are dark, hard metamorphic and igneous rocks, the roots of ancient mountains. Above them lie the sedimentary layers, stacked in order, telling the story of seas that came and went, deserts that formed and eroded, life that emerged and evolved. It is a cathedral of stone, and the silence there is profound. Other famous exposures include the White Cliffs of Dover, made of chalk, a soft limestone formed from the microscopic shells of marine plankton. These cliffs are bright, almost glowing, and they have been a landmark for sailors for centuries. The chalk formed in a warm, shallow sea during the Cretaceous period, and it is so pure and fine-grained that it has been used for writing and drawing for generations. The cliffs are both beautiful and scientifically rich, a reminder that even the softest stone has stories to tell. The Badlands of South Dakota are another remarkable exposure of sedimentary rock layers. Here, erosion has carved the landscape into a maze of ridges, gullies, and pinnacles, all striped with layers of different colors. The layers contain fossils of ancient mammals, including early horses, camels, and saber-toothed cats. The Badlands are a paleontologist's treasure, and their stark beauty has a quiet power. The layers are soft and erode quickly, so the landscape is constantly changing, revealing new fossils and new details. It is a place where the past is always emerging. Rock layers also exist beneath the oceans, hidden from view, but no less important. Ocean drilling projects have brought up cores of sediment from the deep sea floor, revealing layers that record ocean temperatures, currents, and chemistry over millions of years. These cores are like climate records, showing how the Earth's climate has changed in response to shifting continents, changing ocean circulation, and varying levels of greenhouse gases. The deep-sea sediments are fine and undisturbed, accumulating slowly and steadily, making them some of the most complete records we have. The stones beneath the waves are quiet keepers of climate history. Ice cores, though not rock, serve a similar purpose for more recent history. Layers of ice and glaciers trap air bubbles, dust, and isotopes that reveal past temperatures and atmospheric composition. Ice cores from Antarctica and Greenland go back hundreds of thousands of years, complementing the rock record. Together, rock layers and ice layers give us a comprehensive view of Earth's climate history, from the deep past to the recent. The Earth keeps many archives, in many forms, all telling the same patient story. Rock layers also respond to life in surprising ways. Some sedimentary rocks, like certain limestones, are almost entirely biological in origin, made from the shells and skeletons of countless organisms. Reefs, both ancient and modern, are built by living creatures, primarily corals and algae, that secrete calcium carbonate. These reefs become rock layers over time, preserving the structure of the reef and the organisms that live there. Ancient reefs are often rich in fossils and are also important reservoirs for oil and gas. The stones and life are intertwined, each shaping the other. Stromatolites are among the oldest evidence of life on Earth. These layered structures are built by cyanobacteria, which trap and bind sediment in thin layers. Stromatolites were common in Precambrian oceans, and some still form today in a few special places, like Shark Bay in Australia. The layers in stromatolites are incredibly fine, sometimes representing daily or seasonal growth. They are living fossils, a direct link to the earliest life on Earth. The stones remember the very beginning, the first whispers of biology on a young planet. Rock layers also record the oxygenation of Earth's atmosphere. Before about 2.4 billion years ago, Earth's atmosphere contained very little oxygen. Cyanobacteria began producing oxygen through photosynthesis, and over time, oxygen levels rose. This event, called the Great Oxidation Event, is recorded in rock layers. Banded iron formations, layers of iron-rich rock interbedded with chert, formed before the oxygenation. Once oxygen became abundant, iron could no longer accumulate in the oceans in the same way, and banded iron formations stopped forming. The stones mark this turning point, this quiet revolution that made complex life possible. Red beds, sedimentary rocks colored red by iron oxide, are another indicator of oxygen in the atmosphere. They become common in the rock record after the Great Oxidation Event. The red color comes from rust, iron that has reacted with oxygen. Before oxygen was abundant, rocks could not rust in this way. The shift from gray and green rocks to red rocks is a visual marker of the changing atmosphere, a change written in color across the world. The stones turned red, and the world was never the same. Rock layers also show evidence of snowball Earth events, times when the entire planet was covered in ice. These events occurred several times in the Precambrian, and they left distinctive rock layers. Glacial deposits from these times are found in what are now tropical regions, indicating that ice reached the equator. Above these glacial layers are often cap carbonates, thick layers of limestone that formed rapidly as the ice melted and the oceans became supersaturated with calcium carbonate. The sequence of glacial deposits and cap carbonates is a signature of snowball Earth events, a record of the planet's most extreme climate swings. The stones remember even the frozen times, the long silences under ice. Rock layers also preserve evidence of ancient supercontinents. The continents have not always been where they are today. They have drifted, collided, and split apart many times over Earth's history. When continents collide, they create mountain ranges and fold and fault the rock layers. When they split apart, they create rift valleys and new ocean basins. By studying the rock layers on different continents, geologists can piece together the history of continental drift. Rocks of the same age and type, with matching fossils and structures, found on continents now separated by oceans, are evidence that those continents were once joined. The stones are puzzle pieces, and when fitted together, they reveal the ancient maps of Earth. Pangaea is the most recent supercontinent, formed about 300 million years ago and beginning to break apart about 200 million years ago. Before Pangaea, there were other supercontinents: Rodinia, Nuna, Kinnerland. Each assembled and broke apart in a slow cycle called the supercontinent cycle, driven by the movement of tectonic plates. The rock layers record each cycle, each collision and rifting, each mountain range built and eroded away. The stones are patient witnesses to the dance of continents, a dance that continues today, imperceptibly slow but unstoppable. Rock layers also tell us about the age of the Earth itself. By dating rocks using radiometric methods, geologists have determined that the Earth is about 4.54 billion years old. The oldest rocks on Earth are about 4 billion years old, found in Canada and Australia. These ancient stones are rare, as most early crust has been recycled by plate tectonics. But they exist, quiet survivors from the Earth's infancy, and they tell us that even in the earliest times, the processes of rock formation were at work. The stones are older than we can easily imagine, but they are here, solid and real, connecting us to the deep past. Zircon crystals, tiny and durable, are among the oldest materials on Earth. Some zircons are over 4.4 billion years old, nearly as old as the planet itself. Zircons form in igneous rocks and are resistant to weathering, so they survive even when the rocks around them are destroyed. They can be found as grains in much younger sedimentary rocks, little time travelers carrying information from the earliest Earth. By studying the chemistry of ancient zircons, scientists have learned that liquid water existed on Earth's surface very early, perhaps as early as 4.3 billion years ago. The stones, even the tiniest grains, hold profound secrets. Rock layers also remind us of the vastness of geological time. A single layer of sandstone might represent thousands of years of deposition. A sequence of layers might span millions of years. The entire rock record spans billions of years. It is difficult for the human mind to grasp such timescales, but the stones make them tangible. We can touch a rock and know that it is older than any human civilization, older than our species, older than most life on Earth. The stones are humbling in the best way. They put our lives in perspective, reminding us that we are part of something much larger and longer than ourselves. And yet, despite their age, the stones are not static. They are constantly changing, slowly but surely. Erosion wears them down, weathering transforms them, tectonic forces lift and fold them, and new layers are always being deposited somewhere. The rock's cycle continues, endlessly renewing and reshaping the Earth's crust. The stones are patient, but they are not frozen. They move, they change, they respond to the forces around them. They are alive, in a geological sense, part of the dynamic, breathing planet. Rock layers also inspire art and culture. People have always been drawn to stone, using it for tools, for building, for sculpture, for jewelry. The colors and patterns in rock layers have inspired designs and decorations. The permanence of stone has made it a symbol of strength and endurance. Monuments and memorials are made of stone because we want them to last. The stones are part of our cultural landscape, not just our physical one. They are woven into our stories, our myths, our sense of place. Geologists, in studying rock layers, are like historians reading ancient texts. Each layer is a page, each fossil a word, each structure a sentence. The language is written in stone, and it takes patience and skill to read it. But once you learn the language, the stones speak clearly. They tell stories of oceans and deserts, of life and death, of calm and catastrophe. They tell the story of the Earth itself, from its fiery beginning to the present day. And the story is still being written, layer by layer, grain by grain, quietly and without hurry. The beauty of studying rock layers is that the evidence is all around us. You do not need expensive equipment or access to remote locations. Rock layers are exposed in road cuts, in stream banks, in cliffs, in quarries. They are beneath our feet, holding up our cities, shaping our landscapes. The stones are generous, offering their stories to anyone willing to look and listen. All it takes is a little curiosity and a willingness to slow down, to observe, to wonder. And as you rest now, perhaps you can imagine those layers stacked deep beneath you, extending down through time. Each layer a moment, each sequence a chapter, all of it held together in the patient embrace of stone. The earth is old, and it has seen much, and it remembers it all, written in the layers. You are resting on a library, a vast archive of time and change, and it is holding you gently, as it has held everything for billions of years. The stones are beneath you, steady and calm, and they will be there long after you wake. The layers beneath us continue their slow conversation with time, speaking in a language older than words, older than thought itself. Each stratum holds within it not just minerals and grains, but moments, captured instants from epochs so distant they challenge our ability to comprehend. Yet here they rest, patient and unhurried, waiting for those who wish to listen. The stone does not demand attention. It simply exists, layer upon layer, a testament to processes that unfold with such gentleness that no single lifetime could witness their completion. Consider how sedimentary rocks form in environments we can still observe today. Modern beaches accumulate sand grain by grain, just as ancient beaches did hundreds of millions of years ago. River deltas build outward into lakes and seas, depositing sediment in patterns that will one day become rock. Coral reefs grow slowly in warm, shallow waters, their calcium carbonate skeletons destined to become limestone. These processes continue now, as they have always continued, connecting the present moment to the deepest past. When you walk along a shore or beside a river, you are witnessing the same forces that created the rocks beneath your feet, the same patient accumulation that has been occurring since water first pooled on Earth's surface. The concept of actualism, closely related to uniformitarianism, suggests that the same natural laws and processes operating today have operated throughout Earth's history. This principle brings a deep comfort. The forces shaping our world are not chaotic or unpredictable in their fundamental nature. Water flows downhill now as it did 3 billion years ago. Sediment settles according to size and density today as it settled in ancient seas. Crystals form following the same geometric principles. This consistency, this reliability of natural law, creates a framework within which all geological history unfolds. The stone layers are not random accidents, but the inevitable result of physical processes acting over time, processes we can understand, measure, and predict. Within sedimentary sequences, geologists sometimes find features called soil marks, preserved on the undersides of sandstone or siltstone beds. These include flute casts, groove casts, and tool marks, impressions created when currents scoured the muddy seafloor before depositing the overlying sediment. Flute casts are elongated, spoon-shaped depressions that point in the direction of ancient current flow. Groove casts are long, straight marks carved by objects dragged along the bottom. Tool marks are created when shells, wood fragments, or other debris bounce and skip across soft sediment, leaving distinctive patterns. These features, now preserved in stone, allow geologists to reconstruct not just what ancient environments looked like, but how water moved through them, which direction currents flowed, and how energetic those flows were. The bottom of a rock layer can be just as informative as its top. Sedimentary rocks also preserve evidence of bioturbation, the reworking of sediment by living organisms. Worms, clams, crustaceans, and countless other creatures burrow through mud and sand, creating tunnels and chambers that are later filled with sediment of a different composition or color. When lithified, these become trace fossils, distinct from body fossils because they preserve behavior rather than anatomy. A rock surface covered with burrows tells us that the seafloor was oxygenated, that life was abundant, and that the sediment accumulated slowly enough for organisms to colonize it. The degree and style of bioturbation can indicate water depth, oxygen levels, and sedimentation rate. In some rocks, bioturbation is so intense that original sedimentary structures are completely destroyed, homogenizing the sediment into a uniform texture. This too is information, a record of thriving benthic communities that lived and worked the sediment long ago. The study of ichnology focuses specifically on these trace fossils. Different organisms create distinctive burrow patterns. Some burrows are simple vertical shafts, others are U-shaped, still others branch in complex networks. Some traces are horizontal tunnels just beneath the sediment surface, while others penetrate deep into the substrate. The assemblage of trace fossils in a rock layer can be classified into ichnofacies, recurring associations that correspond to particular environmental conditions. The Scalethos ichnofacies, characterized by vertical burrows, typically indicates high-energy shoreline environments. The Cruziana ichnofacies, with its diverse horizontal and inclined burrows, suggests lower-energy shelf settings. The Zoophacos ichnofacies, featuring complex, spiral burrows, often occurs in deep-water environments. These patterns repeat throughout the geological record, providing reliable indicators of ancient water depth and energy levels, even when other evidence is ambiguous. Sedimentary rocks sometimes contain concretions, hard, rounded masses that form within the sediment through localized cementation. Concretions grow around a nucleus, which might be a shell fragment, a piece of organic matter, or simply a spot where chemical conditions favored mineral precipitation. As minerals crystallize from pore water, they cement the surrounding sediment into a hard nodule. Concretions can be spherical, disc-shaped, or highly irregular. They often weather out of softer surrounding rock, littering the ground as mysterious spheres or odd shapes. Some concretions contain exceptionally well-preserved fossils, because the early cementation protected the fossil from compaction and chemical alteration. The famous Mason Creek fossils of Illinois, for example, are preserved within siderite concretions that formed in a freshwater delta environment over 300 million years ago. The concretions captured soft-bodied organisms in exquisite detail, preserving animals and plants that would normally leave no trace. Septarian concretions are particularly striking. These form in a two-stage process. First, a concretion develops in clay-rich sediment. As the sediment compacts and the concretion shrinks or dries, radial and polygonal cracks form within it. Later, these cracks are filled with minerals, often calcite or aragonite, creating a distinctive pattern of veins. When cut and polished, septarian concretions reveal beautiful geometric patterns, with dark clay or mudstone surrounding golden or white crystalline veins. They look almost artificial, like something designed rather than grown, yet they are entirely natural, the product of compaction, dehydration, and secondary mineralization. These objects remind us that nature creates patterns of remarkable complexity and beauty without intention or awareness, simply by following physical and chemical laws. Rock layers also preserve evidence of ancient soils, known as paleosols. When sediment is exposed at the surface for extended periods, weathering and biological activity transform it into soil. Plant roots penetrate downward, organisms burrow through the material, minerals are altered by water and organic acids, and distinctive soil horizons develop. If this soil is then buried by new sediment and lithified, it becomes a paleosol, a fossil soil preserved in the rock record. Paleosols are recognizable by their altered minerals, root traces, burrows, and distinctive color patterns. They indicate pauses in sedimentation, times when the land surface was stable enough for soil to develop. The characteristics of a paleosol can reveal the climate at the time of formation. Well-developed, deeply weathered paleosols suggest humid, warm conditions. Thin, weakly developed paleosols suggest arid or cold climates, or simply brief exposure before burial. Some ancient landscapes preserved multiple stacked paleosols, recording repeated cycles of exposure and burial, each cycle representing thousands or tens of thousands of years. The presence of certain minerals in paleosols provides additional climate information. Kaolinite, a clay mineral, forms through intense chemical weathering in warm, humid environments. Its presence in a paleosol suggests tropical or subtropical conditions. Calcite nodules, in contrast, often form in soils of semi-arid regions where evaporation exceeds precipitation. Iron oxide coatings and nodules indicate oxidizing conditions and often seasonal wetting and drying. By examining the mineralogy, structure, and chemistry of paleosols, geologists can reconstruct ancient climates with surprising precision, adding another dimension to the environmental stories told by sedimentary rocks. Sedimentary sequences sometimes display cyclic patterns called cyclothems, repeated sequences of rock types that reflect cyclic environmental changes. In the coal-bearing rocks of the late Paleozoic, for example, cyclothems typically consist of a basal sandstone, overlain by shale, then coal, then marine limestone, and finally another shale before the cycle repeats. Each cycle represents a complete environmental transition, from river or delta, sandstone, to coastal swamp, coal, to shallow marine, limestone, and back again. These cycles were driven by repeated sea level changes, possibly caused by the growth and melting of glaciers in the southern hemisphere. As ice sheets grew, sea level fell, and rivers and swamps advanced across the landscape. As ice melted, sea level rose, and marine waters flooded the coastal plains. These cycles repeated dozens of times, each one preserved as a distinct cyclothem in the rock record. The regularity of these patterns is soothing in its predictability, a rhythm imposed by astronomical and climatic forces acting over millions of years. In marine settings, similar cyclic patterns occur in response to changes in ocean chemistry, productivity, or circulation. Alternating layers of limestone and shale, for instance, might reflect cycles of high and low carbonate production, driven by variations in nutrient supply or water temperature. Some of these cycles are linked to Milankovitch cycles, periodic changes in Earth's orbit and axial tilt that affect the distribution of solar radiation and drive climate oscillations. These orbital cycles operate on timescales of tens to hundreds of thousands of years, and their signatures can be detected in sedimentary sequences as rhythmic variations in rock type, color, or fossil content. By analyzing these patterns, geologists can not only reconstruct ancient climates, but also calibrate geological time with remarkable precision, counting cycles like tree rings to measure the passage of millennia. Rock layers also contain evidence of catastrophic events, moments when the slow accumulation of sediment was interrupted by sudden, dramatic processes. Volcanic eruptions can deposit thick layers of ash over vast areas in a matter of hours or days. These ash layers, called benenites when altered to clay, serve as valuable time markers because they represent geologically instantaneous events that can be traced across wide regions. Meteorite impacts create distinctive layers containing shocked quartz, spherules, and elevated concentrations of rare elements like iridium. The most famous of these is the Cretaceous-Paleogene boundary layer, which marks the impact event that contributed to the extinction of the dinosaurs. This thin layer, often just a few centimeters thick, can be found on every continent, a global signature of a single catastrophic day 66 million years ago. It reminds us that while most geological processes are slow and gradual, Earth's history also includes moments of sudden, profound change. Turbidites, deposited by underwater landslides, also represent rapid events. A turbidity current can transport enormous volumes of sediment down a continental slope in a matter of hours, depositing a graded bed that might be meters thick. In the deep ocean, where sedimentation rates are typically measured in millimeters per thousand years, a single turbidite can represent more sediment than accumulates over tens of thousands of years of normal deposition. Yet even these catastrophic deposits become part of the layered record, interbedded with the slow, patient accumulation of pelagic sediment. The rock record thus contains both the everyday and the extraordinary, the gradual and the sudden, all preserved in orderly layers that can be read by those who know the language. Sedimentary rocks also preserve evidence of ancient microbial life in the form of stromatolites, layered structures created by the trapping and binding of sediment by microbial mats. Modern stromatolites still form in a few restricted environments, such as the hypersaline waters of Shark Bay in Australia, where high salinity excludes most grazing organisms that would otherwise consume the microbial mats. Ancient stromatolites, however, were once widespread, dominating shallow marine environments for billions of years before the evolution of grazing animals. The oldest stromatolites date back more than 3.5 billion years, making them among the earliest evidence of life on Earth. These structures are simple, just thin, wavy layers of sediment bound by microbial films. Yet they represent one of life's great innovations, the ability to create persistent structures that alter the environment. In a sense, stromatolites are the first reefs, the first ecosystems engineered by living organisms, and their presence in ancient rocks connects us to the very dawn of biology. The study of stromatolites reveals how life and geology are intertwined. The microbes that build stromatolites don't just trap sediment. They also influence water chemistry, precipitating minerals and altering the composition of the surrounding environment. Some stromatolites are rich in calcium carbonate, precipitated directly by microbial metabolism. Others are primarily silica, formed in hot spring environments where microbes mediate the deposition of opaline silica. The shapes of stromatolites, columnar, branching, domal, or flat, reflect the environmental conditions in which they grew, including water depth, current strength, and sedimentation rate. By studying ancient stromatolites, geologists can reconstruct not only the presence of life, but also the specific environmental settings in which that life thrived. These humble, layered structures are windows into ecosystems that existed when Earth was young, when the atmosphere lacked oxygen, and when life was simple but already transforming the planet. Rock layers also contain evidence of ancient deserts, preserved in the form of Aeolian sandstones. These rocks, formed from wind-blown sand dunes, have distinctive characteristics. The cross-bedding is typically large-scale and sweeping, reflecting the shape of migrating dunes. The sand grains are well-rounded and well-sorted, polished by countless collisions during wind transport. The rock may show features like pinstripe lamination, created by the alternation of coarser and finer grains on dune surfaces, or raindrop impressions, formed when rare desert rains pockmark the dune surfaces. Some Aeolian sandstones contain fossilized trackways of reptiles or early mammals, animals that crossed the dunes and left their footprints in the sand. These trackways are often the only evidence of terrestrial life in desert environments, where conditions are generally too harsh for the preservation of body fossils. The Navajo sandstone of the American Southwest, for example, is a vast Aeolian deposit from the Jurassic period, representing a desert that once covered much of what is now Utah, Arizona, and Colorado. Its towering cliffs and sweeping crossbeds are frozen sand dunes, monuments to an ancient arid landscape. The colors of Aeolian sandstones are often particularly striking. Many are shades of red, orange, or pink, colored by thin coatings of iron oxide on the sand grains. These coatings form through oxidation and can develop either during deposition or later, as groundwater moves through the rock. Some Aeolian sandstones display color banding, with alternating red and white layers. The white bands often represent zones where reducing fluids have passed through the rock, stripping away the iron oxide coatings and bleaching the sandstone. These color patterns can create breathtaking landscapes, as seen in places like Zion National Park or the Vermilion Cliffs. The beauty of these rocks is not incidental. It is a direct expression of their chemistry and history, a visual representation of the processes that formed and altered them over millions of years. Sedimentary rocks also preserve evidence of glaciation in the form of tillites and dropstones. Tillites are lithified glacial till, the unsorted, unstratified sediment deposited directly by glacial ice. They contain a chaotic mixture of particle sizes, from fine clay to large boulders, all jumbled together. Many of the larger clasts and tillites are striated and faceted, scratched, and shaped by their transport at the base of a glacier. The presence of tillite in the rock record indicates that glaciers once existed in that location, even if it is now tropical. Dropstones are isolated large clasts found within finely laminated sediments, deposited when icebergs drifted over a lake or ocean and dropped their rocky cargo as they melted. The sudden appearance of a boulder-sized clast in the middle of thinly bedded mud is distinctive and diagnostic. Dropstones are particularly common in rocks deposited during ice ages, when icebergs were abundant. The presence of these features allows geologists to identify ancient glacial periods, even those that occurred hundreds of millions of years ago. Earth has experienced several major glaciations throughout its history. The most extreme were the snowball Earth events of the Neo-Proterozoic era, roughly 700 to 600 million years ago, when glaciers may have extended to or near the equator and ice covered much or all of the ocean surface. Evidence for these events includes tillites and dropstones found in rocks that formed at tropical latitudes, based on paleomagnetic data. The idea of a completely frozen Earth is both unsettling and strangely peaceful. A planet locked in ice, silent and still, for millions of years. Yet life survived, perhaps in refugia near volcanic vents or in pockets of open water. And when the ice finally retreated, life diversified explosively. The Snowball Earth episodes may have been crucial in setting the stage for the evolution of complex animals, demonstrating once again how even the most extreme geological events are woven into the larger story of life. The more recent Pleistocene glaciations, which ended only about 11,700 years ago, also left abundant evidence in the rock record. These ice ages involved repeated advances and retreats of continental ice sheets across North America, Europe, and Asia. The glaciers scoured the landscape, carving valleys, polishing bedrock, and depositing vast quantities of till. In many regions, the bedrock surface still bears the scratches and grooves carved by glacial ice, aligned in the direction of ice flow. These striations are tangible evidence of the immense forces exerted by moving ice, forces capable of reshaping entire continents. The sediments deposited by Pleistocene glaciers form a relatively young and unconsolidated part of the rock record, but they are no less informative than their ancient counterparts. They tell of a world where ice sheets more than a mile thick covered regions that are now temperate, where sea level was more than 100 meters lower than today, and where the climate oscillated between glacial and interglacial states in response to orbital variations. Sedimentary rocks also preserve evidence of ancient river systems in the form of fluvial deposits. Rivers transport sediment from highlands to lowlands, depositing it in channels, floodplains, and deltas. The characteristics of fluvial deposits reflect the behavior of the river that formed them. Braided rivers, which consist of multiple shifting channels separated by bars and islands, deposit coarse-grained, cross-bedded sandstones with erosional bases and frequent channel changes. Meandering rivers, which have a single sinuous channel, deposit fine-grained sediment on floodplains and coarser sediment in point bars on the inside of meander bends. The deposits of meandering rivers often show fining upward sequences, with coarse sand at the base grading upward into silt and clay. Ancient river deposits can be identified by these characteristic patterns, and the architecture of the deposits can reveal the size, discharge, and behavior of the river. Some ancient river systems were enormous, dwarfing any modern rivers, and their deposits extend for hundreds of kilometers, testament to the power and persistence of flowing water. The study of fluvial deposits also reveals how rivers respond to changes in climate, tectonics, and sea level. During periods of high precipitation or glacial melting, rivers carry more water and sediment, depositing thick sequences of sand and gravel. During drier periods, rivers may become smaller or intermittent, and floodplain soils develop. Tectonic uplift can rejuvenate a river, causing it to insize into its own deposits and create terraces. Sea level rise can cause a river to deposit its sediment farther inland, while sea level fall can cause it to extend its channel across the newly exposed shelf. All of these changes are recorded in the rock layers, creating a complex but readable history of landscape evolution. The patience required to decipher this history mirrors the patience of the rivers themselves, which carve their paths grain by grain, year by year, over timescales that stretch beyond human comprehension. Sedimentary rocks also contain evidence of ancient lakes, preserved as lacustrine deposits. Lakes are sensitive recorders of environmental change because they are relatively small, closed systems that respond quickly to shifts in climate, water supply, and sediment input. Lake sediments are typically fine-grained, consisting of clay, silt, and organic matter that settles slowly from the water column. Many lake deposits are thinly laminated, with each layer representing a season or a year. These varves, as they're called, can be counted like tree rings to measure time with annual precision. The thickness and composition of varves vary with climate. Thick, organic-rich layers form during warm, productive summers. Thin, clay-rich layers form during cold, less productive winters. By analyzing varve sequences, geologists can reconstruct past climate variations in remarkable detail, sometimes year by year for thousands of years. Some ancient lakes were enormous, far larger than any modern lakes. During the Mesozoic era, for example, vast lakes existed in what is now China, depositing thick sequences of shale and limestone that now yield abundant fossils of fish, reptiles, and early birds. During the Cenozoic era, large lakes formed in the western United States, including Lake Bonneville, the ancestor of the Great Salt Lake, and Lake Lahontan in Nevada. These lakes expanded during wet periods and contracted during dry periods, leaving behind terraces and shorelines that mark their former extent. The sediments of these ancient lakes contain fossils, pollen, and chemical signatures that reveal the ecosystems and climates of the past. They are archives of environmental change, preserved in layers that can be read by patient observers. Rock layers also preserve evidence of ancient wetlands and peat swamps, environments where organic matter accumulates faster than it decays. In modern swamps, dead plant material piles up and waterlogged, oxygen-poor conditions, forming peat. If this peat is buried and subjected to heat and pressure over millions of years, it transforms into coal. Coal is therefore a sedimentary rock composed primarily of organic matter, a concentrated remnant of ancient forests. The type of coal that forms depends on the degree of metamorphism. Peat transforms first into lignite, then subbituminous coal, then bituminous coal, and finally anthracite. Each stage represents greater heat and pressure, which drive off water and volatile compounds, leaving behind increasingly pure carbon. The presence of coal in a rock sequence indicates that a swamp or wetland existed at that location for a prolonged period, allowing thick accumulations of peat to develop. The coal seams of the Carboniferous period, for example, represent vast coastal swamps that persisted for millions of years, forests of giant ferns, horsetails, and early trees that grew, died, and accumulated in standing water. The fossils found in coal and associated rocks provide a window into these ancient swamp ecosystems. Petrified tree stumps are sometimes found in growth position, rooted in the sediment beneath coal seams, showing exactly where the trees stood. Fossils of amphibians, early reptiles, and giant arthropods reveal the animals that inhabited these swamps. Impressions of leaves, bark, and spores allow botanists to reconstruct the plant communities in detail. These were strange, alien forests, dominated by species that have no modern equivalents, yet they were real places, as real as any modern wetland, filled with life and the sounds of wind, water, and animals. The coal we burn today is the compressed remains of those forests, sunlight captured by photosynthesis hundreds of millions of years ago, stored in carbon bonds, and now released as heat and light. It is a humbling thought, a connection across deep time that links our energy use to ancient ecosystems. Sedimentary rocks also preserve evidence of ancient coral reefs, some of the most diverse and productive ecosystems on Earth. Modern coral reefs are built primarily by scleractinian corals, but ancient reefs were constructed by different organisms at different times. In the Paleozoic era, reefs were built by tabulate and rugose corals, as well as stromatoporoids, sponge-like organisms that secreted calcium carbonate skeletons. In the Permian period, reefs were often dominated by sponges and algae. After the end Permian mass extinction, which wiped out most reef-building organisms, it took millions of years for reef ecosystems to recover. The scleractinian corals that dominate modern reefs first appeared in the Triassic period and have been the primary reef builders ever since. Ancient reef rocks are typically massive limestones with complex internal structures, reflecting the three-dimensional framework created by the reef organisms. These rocks often contain abundant fossils of the organisms that lived in and around the reef, including corals, sponges, mollusks, echinoderms, and fish. The study of ancient reefs reveals how these ecosystems have responded to environmental changes over geological time. Reefs are sensitive to temperature, water chemistry, sea level, and sediment input. During periods of rapid environmental change, reefs often decline or disappear, only to recover when conditions stabilize. The fossil record shows that reef crises have occurred repeatedly throughout Earth's history, often associated with mass extinctions or major climate shifts. Yet reefs have always recovered, albeit sometimes with different organisms taking on the reef-building role. This resilience, This ability to persist and adapt over hundreds of millions of years is both inspiring and sobering. It reminds us that ecosystems can endure immense challenges, but recovery takes time, often millions of years. The rock record teaches patience, both in the slow construction of reefs and in the long timescales of recovery after disruption. Sedimentary rocks also contain evidence of ancient volcanic activity, even in regions far from volcanic centers. Volcanic ash can be transported by wind for thousands of kilometers, settling as a fine dust that forms thin, distinctive layers in sedimentary sequences. These ash layers, or tuffs, are valuable for dating and correlating rock sequences because they represent geologically instantaneous events that can be traced across wide areas. Volcanic ash is also rich in minerals that can be dated using radiometric methods, providing precise age constraints for the surrounding sedimentary rocks. In some cases, volcanic ash alters to clay minerals, forming bentonite layers that are soft and plastic. These layers can serve as lubricants, causing landslides or facilitating the movement of overlying rock layers. The presence of volcanic ash in sedimentary rocks is a reminder that Earth's surface processes do not occur in isolation. They're influenced by the planet's internal heat and the movement of tectonic plates, which generate volcanism and shape the distribution of land and sea. Rock layers also preserve evidence of ancient impact events, though these are rare. Large meteorite impacts are infrequent on human timescales, but inevitable over geological time. When a large meteorite strikes Earth, it creates a crater and ejects enormous quantities of material into the atmosphere. Some of this material falls back to Earth as a global layer of debris, containing shocked minerals, glassy spherules, and elevated concentrations of elements like iridium, which are rare in Earth's crust but common in meteorites. The most famous impact layer is the Cretaceous-Paleogene boundary, but others have been identified at various points in Earth's history. Each impact layer represents a moment of catastrophic disruption, a sudden injection of energy and material that affected the entire planet. Yet, even these violent events become part of the layered record, thin lines in the rock that mark the boundary between one era and the next. Sedimentary rocks also contain evidence of ancient ocean chemistry, preserved in the form of banded iron formations. These distinctive rocks consist of alternating layers of iron-rich minerals and silica, typically red, black, and gray in color. Banded iron formations are most common in rocks older than about 1.8 billion years, and they provide crucial evidence for the evolution of Earth's atmosphere and oceans. The iron in these formations was dissolved in seawater at a time when the oceans were anoxic and iron could remain in solution. When oxygen began to accumulate in the oceans, produced by photosynthetic cyanobacteria, the iron oxidized and precipitated as iron oxide minerals. The banding reflects cyclic changes in ocean chemistry, possibly driven by seasonal or longer-term variations in oxygen production or iron supply. Banded iron formations are thus a record of one of the most important events in Earth's history, the oxygenation of the planet, which paved the way for the evolution of complex life. The study of banded iron formations reveals the intricate interplay between life, ocean chemistry, and atmospheric composition. The oxygen produced by cyanobacteria did not immediately accumulate in the atmosphere. Instead, it reacted with dissolved iron, methane, and other reduced substances, oxidizing them and removing the oxygen from the system. Only after these oxygen sinks were exhausted did oxygen begin to accumulate in the atmosphere, leading to the Great Oxidation event around 2.4 billion years ago. This event transformed Earth, creating an oxidizing atmosphere that was toxic to many anaerobic organisms, but enabled the evolution of aerobic respiration, a far more efficient way of extracting energy from organic matter. The banded iron formations are silent witnesses to this transformation, layers of rust that mark the transition from an ancient, anoxic world to the oxygenated planet we inhabit today. Sedimentary rocks also preserve evidence of ancient hydrothermal systems, where hot, mineral-rich fluids circulated through the crust. These fluids can deposit minerals in fractures and pore spaces, creating veins, nodules, and cements that alter the original rock. Hydrothermal minerals include quartz, calcite, pyrite, and a variety of metal sulfides. In some cases, hydrothermal activity creates or deposits concentrations of valuable metals like gold, silver, copper, or zinc. The presence of hydrothermal minerals in sedimentary rocks indicates that the rocks were once buried deeply enough or located near enough to a heat source for hot fluids to circulate. The study of these minerals can reveal the temperature, composition, and source of the fluids, providing insights into the thermal and chemical evolution of sedimentary basins. Even in rocks that have not been significantly metamorphosed, the subtle signs of hydrothermal alteration can be detected, adding another layer of complexity to the geological story. Rock layers also contain evidence of ancient groundwater flow, preserved in the form of diagenetic features. Diagenesis refers to all the physical and chemical changes that occur in sediment after deposition, but before significant metamorphism. Groundwater moving through sediment can dissolve some minerals and precipitate others, altering the texture, composition, and color of the rock. For example, groundwater carrying dissolved calcium carbonate can cement loose sand into sandstone. Groundwater carrying dissolved iron can create red or yellow staining. Groundwater depleted in oxygen can create reducing conditions that dissolve iron oxides, bleaching the rock. These diagenetic changes are often localized, creating patterns and features that reveal the pathways of ancient groundwater flow. By studying these patterns, geologists can reconstruct the hydrogeology of sedimentary basins, understanding how fluids move through the subsurface millions of years ago. Sedimentary rocks also preserve evidence of ancient earthquakes in the form of seismites, disturbed layers created by ground shaking. When an earthquake occurs, unconsolidated sediment can be liquefied, causing layers to deform, fold, or break. The resulting structures include convolute bedding, lode casts, flame structures, and clastic dikes, features that are distinctive and diagnostic of seismic activity. Seismites are particularly common in lake and marine sediments, where fine-grained, water-saturated sediment is prone to liquefaction. The presence of seismites in a sedimentary sequence indicates that the region experienced earthquakes during deposition, providing evidence of ancient tectonic activity. In some cases, multiple seismite layers occur within a single sequence, recording a history of repeated earthquakes over thousands or millions of years. These features remind us that the solid ground beneath our feet is not as stable as it seems. It shifts, shakes, and deforms, and the rock layers preserve a record of that movement. The study of sedimentary rocks also reveals the role of time in shaping the Earth. Geological processes operate on timescales that are difficult for humans to grasp. A mountain range takes millions of years to rise and tens of millions of years to erode away. A sedimentary basin takes millions of years to fill with sediment. A fossil species might exist for millions of years before going extinct. These timescales are so vast that they seem almost abstract, yet they are real. The rock layers are the evidence, the tangible proof that these processes occur, and that time is the medium through which they unfold. Each layer is a moment, each sequence a chapter, each formation a volume in the great library of Earth's history. To study sedimentary rocks is to become a reader of this library, to learn the language of stone and time, to understand that the present is just one frame in a film that has been running for billions of years. The concept of deep time, introduced by geologist John McPhee, captures this sense of vast duration. Deep time is the recognition that Earth's history extends far beyond human history, beyond the history of our species, beyond the history of our genus, beyond even the history of mammals or dinosaurs. It extends back to the formation of the planet itself, 4.6 billion years ago, a span so immense that it challenges our ability to comprehend. Yet the rock layers make deep time tangible. When you stand before a cliff face and see layers stacked one upon another, you are looking at time made visible. Each layer is older than the one above it, and the entire sequence represents a duration measured in millions of years. The rock does not hurry. It does not rush. It simply is, patient and enduring, a monument to the slow unfolding of geological processes. Sedimentary rocks also teach us humility. They remind us that we are latecomers to this planet, that the Earth existed for billions of years before humans appeared, and that it will continue to exist long after we are gone. The processes that form sedimentary rocks, erosion, transport, deposition, lithification, operated long before we evolved and will continue long after we disappear. The rock layers do not care about human history, human ambitions, or human anxieties. They simply record the passage of time and the operation of natural processes. There is something profoundly calming in this perspective, a reminder that our worries and concerns are small in the context of geological time, that the Earth is patient and enduring, and that the processes that shape it are far larger and more powerful than any human endeavor. Yet sedimentary rocks also connect us to the past in intimate ways. The fossils they contain are the remains of real organisms that lived, breathed, ate, reproduced, and died. The footprints preserved in ancient mud were made by animals that walked across a real landscape, under a real sky, perhaps on a sunny day or a rainy night. The ripples in ancient sandstone were formed by real water, flowing in a real river or lapping on a real shore. These are not abstractions. They are traces of actual events, moments that occurred once and were preserved by chance and circumstance. To study these traces is to reach across time and touch, however briefly, the reality of the past. It is to recognize that the past was as real as the present, that the organisms and environments of deep time were as vivid and complex as those of today, and that we are connected to them through the unbroken thread of Earth's history. Sedimentary rocks also inspire wonder. The sheer diversity of rock types, structures, and fossils is staggering. No two rock layers are exactly alike, yet all follow the same fundamental principles. The creativity of nature, operating within the constraints of physical and chemical law, produces an infinite variety of forms and patterns. A limestone can be fine-grained or coarse, fossiliferous or barren, white or black, massive or bedded. A sandstone can be red or yellow, cross-bedded or horizontally stratified, cemented with quartz or calcite, bearing ripples or burrows or nothing at all. Each variation reflects a unique combination of conditions: source material, transport mechanism, depositional environment, diagenetic history. The study of sedimentary rocks is thus an endless exploration, a journey through landscapes of stone where every outcrop offers new discoveries and new insights. The beauty of sedimentary rocks is not just scientific, it is aesthetic. The colors, textures, and patterns of rock layers can be breathtaking. The red and white stripes of the Vermilion cliffs, the sweeping crossbeds of the Navajo sandstone, the delicate laminations of varved lake sediments, the intricate patterns of fossilized ripples and burrows. All of these are beautiful in their own right, independent of their scientific significance. This beauty is not incidental. It is a direct expression of the processes that form the rocks, a visual representation of geological history. To appreciate this beauty is to see the Earth not just as a collection of resources or a stage for human activity, but as a work of art, shaped by natural forces over immense spans of time. Sedimentary rocks also have practical importance. They host many of the resources that modern society depends on, including fossil fuels, groundwater, and mineral deposits. Coal, oil, and natural gas are all found in sedimentary rocks, formed from the remains of ancient organisms. Aquifers, the underground reservoirs that supply much of our drinking water, are typically composed of porous sandstone or limestone. Sedimentary rocks also contain deposits of salt, gypsum, phosphate, and other minerals used in industry and agriculture. Understanding the formation and distribution of these resources requires a deep knowledge of sedimentary processes, the same processes we have been exploring. The study of sedimentary rocks is thus not just an academic pursuit. It has direct relevance to human well-being and the functioning of modern society. Yet even beyond their practical value, sedimentary rocks have intrinsic worth. They are the archives of Earth's history, the records of past climates, ecosystems, and events. They tell us where we came from, how our planet has changed, and how life has evolved. They provide the context for understanding the present and the basis for predicting the future. Without the rock record, we would have no knowledge of deep time, no understanding of evolution, no awareness of how dynamic and changeable our planet is. The rock layers are not just old stones. They are the memory of the Earth, the accumulated knowledge of 4.6 billion years of planetary history. To study them is to engage with that memory, to become a keeper of knowledge that spans eons. As we reach the end of this gentle exploration, let us take a moment to reflect on what we have learned. We have journeyed through the slow, patient processes that form sedimentary rocks, from the weathering of mountains to the deposition of grains in ancient seas. We have explored the structures and features preserved in rock layers, from ripples and crossbeds to fossils and burrows. We have considered the environments in which these rocks formed, from rivers and deltas to deserts and reefs. We have touched on the history recorded in the rocks, from the oxygenation of the atmosphere to the rise and fall of species and ecosystems. We have seen how rock layers reveal deep time, making visible the vast duration of Earth's history. And we have recognized the beauty, wonder, and significance of these ancient stones, which connect us to the past and teach us about the planet we inhabit. The rock layers beneath us continue their silent witness, recording the present even as we speak. Sediment is accumulating in rivers, lakes, and oceans, grain by grain, layer by layer. In millions of years, these sediments will become rock, and future geologists, if they exist, will study them to understand our time, just as we study ancient rocks to understand the past. The processes that form sedimentary rocks are ongoing, timeless, and universal. They operated in the deep past, they operate now, and they will continue to operate in the distant future. This continuity, this unbroken chain of cause and effect stretching across billions of years, is one of the most profound and comforting truths revealed by the study of geology. So as you prepare to rest, let your mind settle on the image of rock layers, stacked quietly one upon another, each a page in the story of the Earth. Let the slowness of geological processes calm your thoughts. The vastness of deep time put your worries in perspective. The Earth is patient. The rocks are patient. Time unfolds slowly, gently, without haste. There is no urgency in the formation of a sedimentary layer, no anxiety in the flow of a river or the settling of grains on a seafloor. These processes simply happen, as they have always happened, as they will always happen, governed by laws that are constant and reliable. In this constancy, there is peace. In this patience, there is rest. You are safe here, in this moment, on this ancient planet that has seen so much and endured so much. The rock layers beneath you have been forming for billions of years, and they will continue to form long after you are gone. You are part of this story, a brief but real chapter in the ongoing narrative of Earth. Your existence is as valid and as significant as any fossil, any ripple, any grain of sand preserved in stone. You are here, now, and that is enough. The Earth does not demand anything of you. It simply holds you, supports you, and continues its slow, patient work of building and eroding, depositing and lithifying, layer upon layer, age upon age. If you are still awake, know that more stories await, more gentle explorations of the natural world and the processes that shape it. But if sleep is calling, let it come. Let your thoughts drift like sediment settling through water, slowly, softly, finding their place. Let the rhythm of geological time lull you into rest, the deep, slow pulse of a planet that breathes in eons. The rock layers will still be here when you wake, patient and enduring, ready to share their stories whenever you wish to listen. Rest now, knowing that you are held by a planet that is ancient, stable, and kind. The stones beneath you have been here for longer than you can imagine, and they will be here long after you wake. They ask nothing of you, expect nothing of you. They simply are, and in their being, they offer a lesson in patience, endurance, and peace. Let that lesson sink into your mind as you sink into sleep. Let the slow accumulation of sediment, grain by grain, layer by layer, become a metaphor for rest, for the gentle accumulation of peace and calm in your mind and body. Good night, gentle traveler through time and stone. May your dreams be as peaceful as ancient seas, as calm as undisturbed sediment, as enduring as the rock layers that hold the history of the Earth. Sleep well, and know that the world will still be here, patient and kind, when you open your eyes again. The stones are watching over you, silent and steady, as they have watched over this planet for billions of years. Rest in their presence, and let the deep time of geology carry you into the deep rest of sleep. Good night.